Hello there, and welcome to the Cosmographer. Line up every other planet in the solar system side by side, and the whole row fits into the gap between the Earth and the Moon with 4,000 kilometers to spare. That is the smallest distance on this list. Number 16 is a 9.5-year flight that bought 30 minutes of data and then took 15 months to send the pictures home at the speed of a 1980s modem. Number 14 is a spacecraft 25 billion kilometers out, whose signal arrives at a tenth of a billionth of a watt. Number 7 is 24 particles caught in 13 seconds from a star that died before there were any human beings to notice. And the distance at the top of this list is the only one that cannot be given a number at all, and not because it is too large to write down. Over the next 3 hours, we count down 20 distances, from the one that 24 people have crossed to the one that no message will ever cross. Get comfortable and settle in. If falling asleep to numbers this size is your idea of a good night, a quiet like and subscribe genuinely helps this channel reach more people who feel the same way. Because by the end of this countdown, the reason the last distance has no number turns out to be the same reason we know every other one. Let's begin at number 20. Number 20, the Earth and Moon. There is a particular kind of number that arrives in the mind and refuses to convert into anything a person can hold. Astronomy is full of them. We say a figure out loud, the listener nods, and nothing actually transfers. The number was received and it was not understood, and both parties move on politely as though something had happened. This list is an attempt to do the opposite. Over the next 3 hours, we are going to work through 20 distances, from the smallest one any human being has ever physically crossed to the one that cannot be given a number at all. Each one will be built up carefully, with real measurements and the real stories of how those measurements were taken, until the number stops being a number and becomes something you can feel the shape of. The first thing worth saying is that distance in space is not a length. It behaves like one for a while, at the small end, where kilometers still mean something. But as we climb, distance stops describing how far apart two things are and starts describing what has become impossible. It becomes a delay that ends conversation. It becomes a limit on how much information can be sent home. It becomes an energy requirement that no engine can meet. And at the top of the list, it becomes a permanent barrier through which nothing will ever pass again in either direction. So we begin at the bottom, with the only distance on this entire list that has been measured by a human hand. The Moon orbits Earth at a mean center-to-center distance of 384,400 kilometers. Light crosses that gap in 1.28 seconds. That is close enough that a conversation is technically possible, and the recordings from the Apollo missions preserve exactly what that felt like. A question would go up, and about 2.5 seconds later, the answer would come back. Not a delay that broke anything. Just a pause, on every exchange, in every transmission, for 8 days at a time. The orbit is not a circle. At its closest, called perigee, the Moon comes within about 356,500 kilometers. At its farthest, apogee, it withdraws to roughly 406,700. The difference between those two figures is around 50,000 kilometers, which is 4 times the diameter of the Earth, and the Moon travels that whole range and back every single month while looking to us like a fixed object in a fixed place. Here is the comparison that does the most work on this entry. Take the 7 other planets of the solar system and line them up side by side, touching in a single row. Mercury is 4,879 kilometers across. Venus is 12,104. Mars is 6,779. Jupiter is 139,820. Saturn is 116,460. Uranus is 50,724, and Neptune is 49,244. Add all of those together, and you get 380,010 kilometers. Every other planet in the solar system, stacked shoulder to shoulder in a single line, fits into the gap between the Earth and the Moon, with about 4,000 kilometers left over. The gap that every diagram ever printed shows as a small blank space is wide enough to swallow every other world we have. That is the first correction, and there will be many more. What makes this distance unusual is that we know it to within a few millimeters, and we know it that precisely because 3 separate crews left mirrors on the surface. On the 21st of July 1969, Buzz Aldrin set down a panel of 100 fused silica corner cube prisms on the Sea of Tranquility. Apollo 14 added a second array. Apollo 15 added a third, carrying 300 prisms. 2 Soviet Lunokhod rovers placed French-built reflectors of their own. A corner cube has the useful property of returning light back along exactly the direction it came from, regardless of the angle it arrives at. Observatories at McDonald in Texas, at Grasse in France, and at Apache Point in New Mexico have been firing laser pulses at those panels ever since. The numbers involved are worth pausing on. A single pulse contains something like 100,000 trillion photons. The beam spreads on the way out, spreads again on the way back, and on a good night, 1 photon returns. 1. From that single returning particle of light, timed against the moment it left, the distance to the Moon is fixed to within a few millimeters. And what more than 50 years of that ranging revealed is that the distance is not holding still. The Moon is receding from Earth at 3.8 centimeters per year. The mechanism is tidal friction. Earth's rotation drags its own tidal bulge slightly ahead of the Moon's position, and the gravity of that displaced bulge tugs the Moon forward, lifting it into a wider orbit. Earth pays for this in rotation, losing roughly 1.8 milliseconds of day length per century. That loss is recorded in stone. Certain fossil corals lay down growth bands daily and seasonally, and corals from about 400 million years ago preserve years containing roughly 400 days. The days were shorter because the planet was spinning faster, and it was spinning faster because the Moon was closer. Of the 20 distances on this list, this is the only one a listener could watch change within a lifetime, and it changes in one direction only, which is away. There is a loose end here that nobody has fully tied off. Take the present recession rate and run it backwards, and the Moon would have been touching Earth's surface around 1.5 billion years ago. That is far too recent. The Moon is 4.5 billion years old. The resolution involves the fact that tidal friction depends on the arrangement of the continents and the shapes of the ocean basins, both of which have changed enormously over hundreds of millions of years, and the actual history has not been reconstructed in full. One more fact belongs to this entry. The last human being to stand at this distance was Eugene Cernan, who lifted off from the Taurus-Littrow Valley on the 14th of December, 1972. Every person who has left the planet since has stayed within about 400 kilometers of the surface. Compared with the first entry on this list, that is roughly 1,000th of the way. 24 people have crossed this distance. Nobody has crossed the next one. And the next one is about 400 times larger, which does not sound like a great deal until you learn that it is the ruler against which every other number in this entire subject has been measured. Number 19. The Earth and the Sun. The distance from Earth to the Sun is 149,597,870.7 kilometers. That figure is unusually exact for a reason that is easy to miss. Since 2012, it has not been a measurement at all. The International Astronomical Union simply defined it, fixed it as the length of the astronomical unit, and every observation since then has been calibrated against that definition rather than the other way round. Light covers it in 499 seconds. 8 minutes and 19 seconds. The sunlight falling on a person at noon left the surface of the sun while that person was doing something else entirely and had already been traveling for the length of a short walk before it arrived. If the sun stopped producing light at this instant, nothing anywhere on Earth would register the change for another 8 minutes. The sky would stay bright. Plants would keep photosynthesizing. Nobody would know. This is the entry where the list stops being about individual objects and starts being about measurement, because this distance is the ruler. Almost every other number in astronomy, out to the very edge of what can be seen, traces its calibration back to this one length. Stellar parallax is measured against the diameter of Earth's orbit. Cepheid variables are calibrated against nearby stars whose distances came from parallax. Type 1a supernovae are calibrated against Cepheids. Redshift distances are calibrated against supernovae. Get the astronomical unit wrong, and the entire ladder shifts underneath, all the way to the last entry on this list. For most of recorded history, nobody could measure it. Aristarchus of Samos made the first serious attempt in the 3rd century before the Common Era. His method was geometrically sound. At the exact moment the moon is precisely half illuminated, the sun, moon, and Earth form a right-angled triangle, and measuring one of the remaining angles gives the ratio of the two distances. He measured that angle as 87 degrees. The true value is closer to 89.85. That small error, propagated through the trigonometry, gave him a sun about 20 times too close. His method was correct. The instruments to use it would not exist for 2,000 years. Kepler is the sharpest illustration of the problem. By 1619, he had the shape of the solar system exactly right. He knew Jupiter orbited at 5.2 times Earth's distance. He knew Saturn was at 9.5. He could give you the proportions of the whole system to several decimal places, and he could not tell you how far away anything was, because he had a map with no scale bar. The solution came from Edmond Halley in 1716. He worked out that if the planet Venus were watched crossing the face of the Sun from two widely separated places on Earth, the two observers would see it trace slightly different paths, and the difference would give the absolute distance. Halley knew the next pair of transits would occur in 1761 and 1769. He also knew, being 60 years old, that he would not live to see either. So he wrote his method down as a set of instructions addressed to a generation that had not yet been born. They followed the instructions. Hundreds of observers were dispatched to points across the globe in what became the first coordinated international scientific campaign in history. Astronomers went to Siberia, to Hudson Bay, to Madagascar, to the Cape of Good Hope. Captain Cook's first voyage to the Pacific, which set out in 1768, existed primarily to place an observer on Tahiti for the second transit. The campaign also produced one of the more difficult stories in the history of the subject. Guillaume le Gentil left France in March 1760, headed for Pondicherry on the Indian coast. War with Britain closed the port and rerouted his ship. On the 6th of June 1761, the transit occurred while he was still at sea, and although the sky was clear, he could see it perfectly and measure nothing, because timing to the required precision is impossible from the deck of a moving vessel. Rather than return home, he decided to wait for the second transit. 8 years. He spent them productively, mapping coastlines, making observations, building a small observatory at Pondicherry, specifically so that he would be ready. On the morning of the 4th of June 1769, the sky over Pondicherry was clear. It had been clear for weeks. Minutes before the transit began, a single cloud moved across the sun. It stayed until minutes after the transit ended, and then it cleared again, and the sky was perfect for the rest of the day. He set out for home. Dysentery held him up for a year. A storm wrecked his ship. He finally reached France in 1771, 11.5 years after leaving, and found that he had been declared legally dead. His estate had been divided among his heirs. His seat at the Academy of Sciences had been given to someone else. It took the intervention of the king to restore his position, and he did eventually recover, remarry, and live another 2 decades. But the 11.5 years brought nothing at all. The transits did produce discoveries that nobody had gone looking for. Mikhail Lomonosov, watching from St. Petersburg in 1761, noticed a thin luminous ring appear around the black disk of Venus at the moment it touched the edge of the Sun. He interpreted it correctly as sunlight refracting through an atmosphere, and in doing so became the first person to detect an atmosphere on another world. The campaign also ran into an obstacle that would frustrate the method for the next 2 centuries. At the moment Venus's disk touches the inner edge of the Sun, the 2 edges appear to stretch toward each other and join, as though connected by a dark ligament. Observers called it the black drop. It makes the precise instant of contact impossible to fix, and different observers watching the same transit through different telescopes disagreed by tens of seconds. Tens of seconds, propagated through the geometry, translated into millions of kilometers. The effect was not explained until 2004, when observations of a Mercury transit from a spacecraft above the atmosphere showed it to be a combination of atmospheric blurring and the telescope's own optical limits, not a real feature of either body. There is also something worth noting about the light itself. Sunlight takes 8 minutes and 19 seconds to reach us, but the energy carried in that light is far older than the trip. Produced by fusion in the solar core, it random walks outward through a plasma so dense that a photon travels only a fraction of a centimeter before being absorbed and re-emitted in a new direction. Estimates for how long that process takes run from around 10,000 years to something over 170,000. The journey from the Sun's surface to your eye takes 8 minutes. The journey from the Sun's center to its surface takes longer than the entire history of agriculture. The campaign as a whole worked. By 1771, Jérôme Lalande had combined the observations into a value for the solar parallax that put the Sun at around 153 million kilometers, within about 2% of the modern figure. The transit method held as the best available approach for nearly 2 centuries, until radar began bouncing pulses off Venus in the early 1960s and fixed the number to within a few hundred kilometers in an afternoon. There is one more thing to say about this distance, and it is that we have now been inside it in a way nobody expected to manage. On the 24th of December 2024, the Parker Solar Probe passed 6.1 million kilometers above the Sun's visible surface. It was moving at 692,000 kilometers per hour, the fastest any object built by human beings has ever traveled. To scale that, if the whole Earth-to-Sun distance were reduced to 1 meter, Parker's closest approach put it 4 centimeters from the surface. It survived because an 11-centimeter shield of carbon composite reached about 1,370 degrees Celsius on the front face, while the instruments tucked behind it stayed near 30. Of the 20 distances on this list, this is the only one we have deliberately made shorter. But the next entry is the one that everyone pictures as the most crowded place in the solar system, and it turns out to be the emptiest thing anything of ours has ever crossed. Number 18. The crossing of the asteroid belt. The main asteroid belt sits between roughly 2.2 and 3.2 astronomical units from the Sun. In kilometers, that is a shell about 150 million kilometers thick, wrapped around a circumference of several billion. Inside it are somewhere over 1 million objects larger than a kilometer across, and estimates for objects larger than 100 meters run into the tens of millions. Every illustration of this region ever produced is wrong in the same specific way. It shows a dense river of tumbling rubble, close packed, with rocks colliding in the background and a spacecraft threading through the gaps at high speed. That picture has been in films, in textbooks, on the covers of magazines, and it has shaped what almost everybody believes about the region. The real numbers invert it completely. The total mass of the entire asteroid belt is about 3% of the mass of the Moon. Ceres alone accounts for roughly a third of that, and the four largest objects together account for over half. Everything else, all million-plus of the kilometer-scale bodies, shares out a remainder smaller than a modest moon. Now spread that material through the volume it actually occupies. The average separation between neighboring objects larger than a kilometer works out to something on the order of 1,000,000 kilometers, which is around 3 times the distance from Earth to the Moon. Put a spacecraft down on a randomly chosen belt asteroid and look around. In most cases, the nearest comparable asteroid would not be visible to the naked eye. It would be a point of light among other points of light, if it could be picked out at all. The belt is a crowd in the same sense that a dozen people scattered across a continent are a crowd. This was not obvious in advance, and the people who had to act on it did not have the luxury of hindsight. When Pioneer 10 was being prepared in the late 1960s, the belt was regarded as a genuine hazard. Estimates of the small particle population varied by orders of magnitude, and mission planners could not rule out the possibility that the probe would be destroyed in transit. It carried meteoroid detectors partly to find out. Pioneer 10 entered the belt in July 1972 and left it in February 1973, having recorded no damaging impacts of any kind. Pioneer 11 repeated the result the following year. Every mission since has confirmed it. Voyager 1 and Voyager 2 crossed. Galileo crossed twice and stopped along the way to photograph 2 asteroids. Cassini crossed. Juno crossed. New Horizons crossed. Dawn went in and orbited 2 of the largest bodies. Lucy and Psyche have both made the passage in the last few years. More than a dozen spacecraft have now gone through the region that was once considered a serious threat to any mission that attempted it. The number of spacecraft lost to asteroid impact in the belt stands at 0. The largest object in the belt has a history that says something about how the region was understood. Giuseppe Piazzi, observing from Palermo on the 1st of January 1801, found a moving point of light where a planet had been predicted to be. Ceres was classed as a planet, and it stayed a planet for about half a century until the discovery of Pallas, Juno, Vesta, and then dozens more made the category untenable. Ceres is 940 kilometers across, round under its own gravity, and probably holds more fresh water than Earth does, locked up as ice beneath its crust. 2 of these bodies have been visited properly. The Dawn spacecraft, using ion engines that produce about as much thrust as the weight of a sheet of paper but can run for years, went into orbit around Vesta in 2011, spent 14 months there, then left and went into orbit around Ceres in 2015. It remains the only mission ever to orbit 2 separate bodies beyond Earth, and the only reason it could was that its engine could be left running almost continuously for the better part of a decade. 2 more missions are out there now. Lucy, launched on the 16th of October 2021, will visit 11 asteroids by 2033, including the Jupiter Trojans that sit 60 degrees ahead of and behind the planet in its orbit. Psyche, launched on the 13th of October 2023, is heading for a body that may be the stripped metallic core of a shattered protoplanet and will arrive in 2029. Some of the belt arrives here without our help. About 4% of meteorites that fall on Earth are carbonaceous chondrites, primitive material from the outer part of the belt that has never been heated above a few hundred degrees since it formed. They carry amino acids, water bound into clay minerals, and grains that predate the solar system entirely. The most thoroughly emptied region of the inner solar system is also the one that keeps posting us samples. Inside the emptiness, there is structure, and it was noticed remarkably early. In 1866, Daniel Kirkwood examined the orbital distances of the roughly 90 asteroids known at the time and found that the distribution had holes in it. Not fewer objects at certain distances, but essentially none. The gaps sat at very specific places, and those places corresponded to simple whole number relationships with Jupiter's orbit. The mechanism is repetition. An object orbiting at 2.5 astronomical units completes exactly 3 orbits in the time Jupiter completes 1. That means Jupiter tugs it at the same point in its path, in the same direction, on every third circuit. One tug does nothing. 10,000 identical tugs, applied at the same point over millions of years, stretch the orbit until it becomes unstable and the object is thrown somewhere else. The 3-to-1 gap sits at 2.5 astronomical units, the 5-to-2 at 2.82, the 7-to-3 at 2.95, and the 2-to-1 at 3.28. The Kirkwood gaps were the first structure anyone recognized in the solar system that was carved by absence rather than by presence. There is a real open question here, and it is about why there is so little material in the first place. Standard models of the young solar system predict that the zone between Mars and Jupiter should have accumulated enough solid material to build a planet several times the mass of Earth. What is actually there is less than 1,000th of Earth. Somewhere between 99.9 and 99.99% of the original material is missing. The leading explanation involves Jupiter forming early and migrating inward toward the Sun before turning around and moving back out, sweeping resonances through the region and scattering most of its contents outward or into the Sun. The broad picture has support. The details are argued over, and the amount of original mass removed is not settled. So the region that everybody imagines as a dense field of rubble is in fact the most thoroughly emptied part of the inner solar system, and its emptiness is itself a piece of evidence about something violent that happened 4.5 billion years ago. This is worth carrying forward, because it is the first appearance of a pattern that will hold for the rest of the list. At every scale we examine, the gap turns out to be the substance, and the objects turn out to be the exception. It will be true of the space between stars. It will be true of the space between galaxies. And at the largest scales of all, it will turn out that the emptiness is not the background against which the universe is arranged. It is the arrangement. Past the belt, the outer solar system begins, and there the unit of distance stops being minutes and becomes hours. Number 17, the first Lighthouse. Jupiter orbits at 5.2 astronomical units, about 778 million kilometers from the Sun. Saturn sits at roughly 9.5 astronomical units, some 1.43 billion kilometers out. Sunlight reaches Jupiter in about 43 minutes and reaches Saturn in about 79. This is where the unit of measurement changes. Everything before this entry could be described in light seconds or light minutes, and a delay measured in minutes is an inconvenience. Past Jupiter, the delay becomes a structural fact about how missions have to be designed, and the design of every outer solar system spacecraft is shaped more by that delay than by anything else. Consider what the Saturn number actually means in practice. During the Cassini mission, a command leaving the Deep Space Network took somewhere between 68 and 84 minutes to arrive, depending on where Earth and Saturn were in their orbits. The acknowledgement took the same time coming back. A single round trip ran to roughly 2 hours and 40 minutes. There is no version of remote control at that range. There is no version of noticing a problem and correcting it. Whatever is happening at the spacecraft has already happened, and the first anyone hears of it is more than an hour later. The clearest demonstration came on the 1st of July 2004. Cassini had to slow down enough to be captured into Saturn orbit, and the only way to do that was a 96-minute engine burn that had to work correctly on the first attempt. If it underperformed, the spacecraft would sail past Saturn and out of the solar system. If it overperformed, it would fall somewhere it was not supposed to be. To make matters more interesting, the burn was executed while the spacecraft flew upward through a gap between two of Saturn's rings, with the 4-meter high-gain antenna turned forward to act as a shield against ring particles. Turning the antenna forward meant it was not pointed at Earth. So, for the most consequential 96 minutes of the mission, the spacecraft was not merely uncontrollable. It was silent. The team on the ground watched the clock and waited, and when telemetry resumed and the numbers came in, they were applauding an event that had finished more than an hour earlier. Everyone in that room was reacting to a recording. The spacecraft had flown the whole maneuver on its own, from a sequence written and uploaded weeks in advance. Getting there is a second kind of distance, and it is the one that surprises people who expect space travel to resemble travel. Cassini launched on the 15th of October, 1997, and did not arrive until July 2004. 6 years and 8 months. And it did not go anywhere near a straight line. The route carries the abbreviation VVEJGA, which stands for Venus, Earth, Jupiter Gravity Assist. Cassini flew inward toward Venus, swung past it, came back and swung past it again, returned to pass close by Earth in August 1999, and then went out to Jupiter for a final push in December 2000. To reach Saturn, in other words, the spacecraft first had to fly toward the Sun. The total path length came to about 3.5 billion kilometers to close a gap of 1.4 billion. Distance in the outer solar system is not really measured in kilometers. It is measured in the change in orbital energy required to get there, and the cheapest route by that measure is almost never the shortest one on a map. The Huygens probe put a precise number on what the delay costs. Huygens separated from Cassini on Christmas Day, 2004, and coasted for 3 weeks. On the 14th of January 2005, it entered Titan's atmosphere, deployed parachutes, and descended for 2 hours and 27 minutes, photographing and sampling as it fell. It survived the landing and kept transmitting from the surface for another 70 minutes. Every part of that was autonomous. There was no possibility of intervention and no possibility of observation. Cassini recorded the data and relayed it onward, and the first images reached Earth after Huygens had already been sitting on the surface of Titan for over an hour. There is a detail in the Huygens story that shows how thin the margins were. The probe transmitted on 2 independent channels for redundancy. In 2000, 5 years after launch and 4 years before arrival, a team ran an in-flight test using a signal from a ground station and discovered that the receiver design had not properly accounted for the Doppler shift caused by the probe's speed relative to the orbiter. The receiver would have locked onto a carrier tone and then failed to decode the data riding on it. The fix could not be a software patch because the hardware was 400 million kilometers away and sealed. Instead, the mission redesigned Cassini's flyby geometry to reduce the relative velocity during the descent. It worked. One channel then failed anyway for an unrelated reason, and roughly half the planned images were lost. The Galileo probe's entry into Jupiter is the most severe version of the same constraint. On the 7th of December 1995, it struck the top of Jupiter's atmosphere at 47.4 kilometers per second. It decelerated at 228 times Earth gravity, which is beyond anything a human body could survive by a very wide margin. Its heat shield lost about half its mass in the process. It then transmitted for 58 minutes as it sank, reporting winds, temperature, composition, and the odd finding that the atmosphere it entered was much drier than expected, before the rising pressure ended it. Every decision it made alone, 43 light minutes from the nearest person who cared about the outcome. The pictures Huygens returned from the surface are worth describing because there are no others like them. They show a flat, damp plain under an orange sky, scattered with rounded pebbles a few centimeters across. The pebbles are water ice, hard as rock at 94 Kelvin, and they are rounded because something has been tumbling them. The something is liquid methane. The probe's heat, sinking into the ground where it landed, boiled methane out of the soil beneath it. Those remain the only photographs ever taken from the surface of a world in the outer solar system, and the mission that delivered them had one shot and no way to check its work. The ground segment that makes any of this possible deserves a mention of its own. The Deep Space Network's 3 70-meter antennas sit at Goldstone in California, near Madrid and near Canberra, spaced roughly 120 degrees apart in longitude. The spacing is deliberate. As Earth rotates, a spacecraft in any direction stays in view of at least one of them continuously. Without that arrangement, every outer system mission would go silent for 8 hours out of every 24. Cassini's own ending shows what the delay does to the last decisions of a mission. Between April and September 2017, it made 22 dives through the gap between Saturn and its innermost ring, a region no spacecraft had entered. Then, on the 15th of September, it was deliberately flown into Saturn's atmosphere and destroyed. The reason was contamination. Cassini had found liquid water at Enceladus and a chemistry at Titan that nobody wanted to risk, and the only way to guarantee the spacecraft could never drift into either of them after its fuel ran out was to remove it from the system entirely. It transmitted until the atmosphere tore it apart, and the final signal took 83 minutes to arrive at an antenna in Canberra from a spacecraft that had already been gone for over an hour. There is a piece of history hidden in this same distance that is worth mentioning because it is where the speed of light was first measured at all. In 1676, Ole Rømer was timing the eclipses of Jupiter's moon Io, which passes behind the planet on a very regular schedule. He noticed that the eclipses ran progressively late when Earth was moving away from Jupiter, and progressively early when Earth was approaching, by up to about 22 minutes over the course of a year. He realized the discrepancy was not in Io's orbit, but in the travel time of the light, which had to cross a longer or shorter gap, depending on where Earth was. That was the first demonstration that light has a finite speed, and it was made using exactly this distance. Everything on the rest of this list, every light year and every look-back time, ultimately rests on a 17th century observation of a moon disappearing slightly late. Past Saturn, the delays keep growing, and the next entry adds a second problem that nobody thinks about until they run into it. It is not how long it takes to get there. It is how long it takes to send the answer home. Number 16. The Sun. To Pluto. Pluto's orbit is eccentric enough that its distance from the Sun swings between about 4.4 and 7.4 billion kilometers over its 248-year circuit. The average is close to 5.9 billion, which is 39.5 astronomical units. Sunlight takes about 5.5 hours to get there. It is worth being accurate about what that means for the light. Noon on Pluto is not darkness. The Sun at that distance is still by far the brightest thing in the sky, a fierce point rather than a disk, delivering roughly the illumination Earth receives about 10 minutes after sunset. Dim by our standards. Bright enough to read by. On a world where the surface temperature runs around -229 degrees Celsius. New Horizons launched on the 19th of January 2006 on an Atlas V with a solid-fuel third stage bolted on top and left Earth at 16.26 kilometers per second. That remains the highest launch speed ever achieved by a spacecraft departing this planet. It crossed the orbit of the Moon in 8 hours and 35 minutes. Apollo took 3 days to cover the same gap. New Horizons did it in a working day, and it was not stopping. It carried something with it. Bolted inside the upper deck is a small aluminium container holding about 30 grams of the ashes of Clyde Tombaugh, who found Pluto on the 18th of February 1930, working as a 24-year-old assistant at the Lowell Observatory with a blink comparator and enormous patience. He died in 1997, 9 years before the launch. The inscription his family chose is on the container. He is the only person whose remains have traveled beyond Neptune. Then it flew for 9 years and 6 months, and it did not spend all of that time awake. Roughly 2/3 of the cruise was spent in hibernation, with most systems powered down and a weekly beacon tone confirming that the spacecraft was still healthy. It woke for annual checkouts. The reason was partly wear on the components and partly the cost of keeping a team of controllers watching a spacecraft that was doing nothing for years at a stretch. There was one exception early on. On the 28th of February 2007, it passed Jupiter for a gravity assist that added about 4 kilometers per second to its speed and cut roughly 3 years off the journey, and it spent that encounter fully awake, photographing the moons and the ring system on the way through. It passed 12,500 kilometers above Pluto's surface on the 14th of July 2015, moving at 13.8 kilometers per second. And here is the part of the encounter that resists intuition entirely. Because the spacecraft had no way to slow down, the window during which Pluto filled the instruments and the highest resolution data could be gathered lasted about 30 minutes. 9.5 years of flight. More than a decade of mission development before that, including a fight for funding that saw the project cancelled and revived more than once. An entire professional generation of careers, some of them started and finished inside the mission. For roughly half an hour of prime observation. During that half hour, nobody on Earth could help. At 4.5 light hours, a round-trip conversation took 9 hours. The spacecraft executed 461 separate commands from a stored sequence, spinning between targets, switching instruments, pointing and repointing, entirely on its own judgment of a clock. There was a genuinely difficult silence in the middle of all this, and it happened 10 days before arrival. On the 4th of July 2015, the main computer was simultaneously compressing 63 images and receiving the enormous encounter command sequence being uploaded from Earth. It could not do both. It overloaded, switched to the backup processor, and dropped into safe mode. Contact was lost for 1 hour and 21 minutes. When the signal came back, the team faced a 9-hour round-trip delay, a spacecraft that had shut down its science instruments, and 10 days before the only opportunity anyone would ever get. They diagnosed the fault, rebuilt the sequence, and uploaded it. Full operations resumed on the 7th of July, with 3 days to spare. Then came the second distance problem, and it is the one that almost nobody anticipates. New Horizons collected about 6.25 gigabytes of data during the encounter. That is less than a modern phone holds in ordinary photographs. Its transmitter runs at 12 watts. By the time the signal reached the 70-meter dishes of the Deep Space Network, the usable data rate was between about 1 and 2 kilobits per second, which is roughly the speed of a telephone modem from the early 1980s. Downlinking the encounter took 15 months. The last bits of Pluto data arrived on the 25th of October 2016, more than a year after the spacecraft had already passed, and while it was already most of the way to its next target. For 15 months, the highest resolution images of Pluto that had ever existed were sitting in a solid-state recorder 5 billion kilometers away, coming home a few kilobits at a time, in whatever order the schedulers had decided mattered most. Stand aboard the spacecraft for a moment on the morning of the 14th of July. It is moving at nearly 50,000 kilometers per hour, and it is entirely alone. Pluto has been a smudge for months, then a disk, then a world with markings, and now it swells until it fills the field of view. The spacecraft rotates on its stored schedule, swinging instruments across the surface, across Charon, across the atmosphere backlit by a sun 5.5 hours behind it. Nothing is being transmitted. The high-gain antenna is pointed at the target, not at home, because pointing it home would mean not looking. For those 30 minutes, the machine is doing the most important work of its existence and is not telling anyone about it. 4.5 light hours away, a room full of people is watching a countdown clock and applauding on schedule at an event that has already been over for hours, with no confirmation that any of it worked. The signal that says the spacecraft survived is not due for another 13 hours. What Pluto turned out to be made the arithmetic worthwhile. There are nitrogen ice glaciers flowing across a plain 1,000 kilometers wide called Sputnik Planitia, and the surface of that plain is divided into convection cells 20 to 40 kilometers across, like the top of a very slow pan of soup. There are mountains of water ice up to 3,500 meters high, water ice being the only material rigid enough at those temperatures to hold up a mountain. There is a haze layer reaching 200 kilometers up, arranged in about 20 distinct strata that nobody predicted. And there are regions with essentially no impact craters at all, which means those surfaces have been renewed within the last 10 million years. That is the finding that mattered most. Pluto is geologically active. On a world that's small, that cold, and that far from any obvious source of heat, something is still moving. The leading explanation involves a subsurface liquid water ocean beneath Sputnik Planitia, which is not what anyone expected to find at 39 astronomical units. Sputnik Planitia also sits almost exactly on the axis facing Charon, which is unlikely to be coincidence. The most plausible reading is that the basin filled with dense nitrogen ice, and the extra mass slowly reoriented the entire world until the heavy spot lined up with the tidal axis. Pluto rolled over to accommodate it. Pluto also does not travel alone in the way the other planets do. Charon is more than half Pluto's diameter, and the two are close enough in mass that they do not orbit a point inside Pluto at all. Their common center of gravity sits in open space between them, and both bodies swing around it. They are also mutually tidally locked, each permanently showing the same face to the other. From one hemisphere of Pluto, Charon hangs motionless in the sky, 7 times wider than our moon appears from Earth, never rising and never setting. From the other hemisphere, it is never visible at all. The best images from the encounter resolve features about 70 meters across. That number deserves a moment. 70 meters from a spacecraft moving past at nearly 50,000 kilometers per hour, at a distance where the light itself takes 4.5 hours to make the trip, using a telescope small enough to lift with 2 hands, sending the result home at the speed of a 1980s modem. And Pluto, for all of that, is not the farthest thing we have ever looked at closely. Number 15. The farthest place we have ever visited. On the 1st of January 2019, at 33 minutes past 5 in the morning Universal Time, a spacecraft passed 3,500 kilometers from an object 6.6 billion kilometers from the Sun. The object is called Arakoth, a Powhatan word meaning sky, chosen with the consent of Powhatan elders and formally assigned in November of that year. It sits at about 44.6 astronomical units, and it remains the most distant object ever examined at close range by anything human beings have built. The light delay at the encounter was 6 hours and 8 minutes each way. Controllers sent the final commands and then had no way of learning whether the flyby had worked for more than 12 hours. The confirmation signal, when it eventually arrived, had spent longer in transit than most people spend at work. The strangest thing about this entry is that the target did not exist when the mission left. New Horizons launched in 2006 with no Kuiper Belt object selected. The plan was to find one during the cruise. This was not recklessness so much as necessity, because the spacecraft had only a small reserve of fuel and could only reach objects inside a very narrow cone of sky that would not be determined until after the Pluto encounter fixed its trajectory. Ground-based searches ran for years and found nothing suitable. The window was closing. The object was finally located on the 26th of June 2014 by a dedicated survey using the Hubble Space Telescope. It appeared as a moving point at magnitude 26.8. To put that in proportion, it is roughly 4 billion times fainter than the dimmest star a person can see on a dark night. Finding it required searching a crowded region of sky toward the galactic center, where the background stars are so dense that a faint moving dot is very nearly impossible to separate from the noise. Even then, almost nothing was known about it. In 2017, teams deployed portable telescopes to Argentina and to Senegal to watch Arakoth pass in front of a background star. 24 mobile stations were set up. Most saw nothing because the shadow track on Earth's surface is narrow and the position was uncertain. A handful of them caught the star blinking out for a fraction of a second, and from the pattern of those few detections, the team worked out that the object was not a sphere, but two lobes joined together. That was the picture they had going in. There was also the question of fuel. After the Pluto encounter, New Horizons had roughly 33 kilograms of hydrazine left in its tanks. That sounds like a reasonable amount until you work out what it buys at 5 billion kilometers, which is a course change of a few tens of meters per second. The reachable region was therefore not a volume of space, but a thin cone extending forward along the existing trajectory, and any candidate object had to be sitting inside it. 4 course correction burns in late 2015 committed the spacecraft to the target, spending most of what remained. The object went through a naming episode along the way. A public campaign in 2018 settled on the informal nickname Ultima Thule, a phrase from classical geography meaning a place beyond the known world. The name drew objections for its later associations, and when the formal designation was assigned in November 2019, the team chose Arakoth instead, in consultation with representatives of the Powhatan people, whose historical territory includes the ground the Hubble Space Telescope's Operations Center stands on. Arakoth turned out to be 36 kilometers long. The larger lobe is about 21 kilometers across and flattened like a pancake. The smaller is about 15, and the critical result was in the geometry of the join. The two lobes are aligned along a common axis. The neck between them shows no compression fracturing. The surfaces on either side of the contact are undeformed. They did not collide. They settled together at a relative speed of a few meters per second, which is walking pace, and they have stayed that way for 4.5 billion years. This mattered more than the shape. For decades, the leading models of how planets begin had planetesimals forming through violent collisions, with objects smashing into each other and occasionally sticking. Arakoth is direct evidence for the alternative, that clouds of pebble-sized material collapsed gently under their own gravity, formed two bodies in a slow mutual orbit, and let orbital decay bring them together over a long time at almost no speed at all. It is the first proper look anyone has had at the assembly stage of planet formation, preserved because nothing has happened to it since. The surface is deep red, colored by tholins. These are complex organic compounds produced when ultraviolet light and cosmic rays work on simple ices over billions of years, and they coat much of the outer solar system. There is methanol ice on Arakoth and no detectable water ice, which was not expected. The temperature is about 40 degrees above absolute zero. There is one more result that says something about the emptiness out there. Arrokoth has almost no craters. Not few craters. Almost none, particularly at small sizes. That means the outer Kuiper belt contains far fewer small objects than the models predicted, and that collisions in that region are rarer than anyone had assumed. The place is emptier than the emptiness we had already accounted for. Arrokoth belongs to a category called the cold classical Kuiper belt objects. These sit on nearly circular orbits with very low inclinations, and the current understanding is that they have never been scattered, never been thrown inward by a giant planet, never been meaningfully disturbed since the solar system formed. Almost everything else out there has a history. This population does not. It is the least processed material a spacecraft has ever been able to reach, which is why one flyby of one small object changed the models. It also rotates in an odd way. Arrokoth turns once every 15.9 hours, and its rotation axis lies almost in the plane of its orbit, so the object is effectively tipped on its side. One lobe points at the sun for decades at a time. The consequence is that the two ends experience very different heating cycles, and the surface chemistry may differ between them in ways a single fast flyby could not fully resolve. New Horizons is now beyond 60 astronomical units and still working. It continues to measure the dust environment, the charged particles, and the brightness of the sky itself, and it has reported that the dust density did not fall off where the Kuiper belt was supposed to end, which hints that the belt extends farther than assumed. Its plutonium supply will run down in the late 2030s. There is no approved successor mission. There is no realistic prospect of another close look at anything beyond 40 astronomical units within the working career of anyone currently planning missions. Whatever else is out there, and there is a great deal, will be observed from a distance or not at all. So here is the summary of this half of the list. Everything humanity has ever physically inspected, every world, moon, comet, asteroid, and fragment we have photographed from close range, fits inside a sphere 45 astronomical units in radius. The next entry crosses that entire sphere in a single day. Number 14, one light day. Voyager 1 left Earth on the 5th of September 1977 and has not stopped since. It is now more than 25 billion kilometers from the Sun, past 168 astronomical units, receding at 17 kilometers per second. That works out to about 535 million kilometers per year, every year, without a single course correction to keep it going. On the 18th of November, 2026, it becomes the first object built by human beings to sit one full light day from home. A signal leaving it on a Wednesday morning arrives here on a Thursday morning. The number that makes this distance real is not the kilometers. It is the power budget. Voyager's transmitter radiates 22 watts. That is comparable to the bulb in a refrigerator. It goes out through a 3.7-meter dish, which focuses it, but a focused beam still spreads. By the time that signal has crossed 25 billion kilometers, it has expanded across a sphere so large that the fraction intercepted by a 70-meter antenna on Earth is almost incomprehensibly small. The power arriving is on the order of 1/10 of a billionth of a billionth of a watt. There is a comparison that is often quoted and is worth stating precisely because it is accurate. The total energy collected by the Deep Space Network from all deep space missions across the entire history of spaceflight amounts to less than the kinetic energy of a single snowflake landing on the ground. Everything ever learned from the outer solar system arrived in less energy than that. The signal remains readable because it is narrowband, because its frequency is known to extraordinary precision, and because the receiver can integrate it over long periods and pull it out from underneath the noise. It is not a strong signal being heard. It is a very weak, very predictable signal being reconstructed. Voyager 1 crossed the heliopause on the 25th of August, 2012, at about 121 astronomical units. There was no marker and no boundary anyone could see. What happened was a swap of populations. The count of low-energy charged particles streaming out from the Sun dropped essentially to zero, and at the same time, the count of galactic cosmic rays coming in from the rest of the galaxy climbed by about 9% and stayed there. That was the crossing. It took months of argument before the team was willing to announce it, because the magnetic field direction did not change the way models had predicted it would. Voyager 2 crossed on the 5th of November 2018 at about 119 astronomical units, and it had an advantage. Its plasma instrument was still functioning, so it could measure the interstellar medium directly. It found a plasma density of roughly 1/10 of a particle per cubic centimeter, about 40 times denser than the solar wind at that distance, and still an emptiness beyond anything achievable in a laboratory. The reason Voyager 1 is out there at all, rather than at Uranus or Neptune, comes down to a single decision made in 1980. The mission had a choice: send Voyager 1 past Titan for a close look at the only moon in the solar system with a thick atmosphere, or keep it in the plane of the planets for a possible later encounter. They chose Titan. The flyby in November 1980 bent the spacecraft's path sharply upward out of the ecliptic plane, ending any possibility of visiting another world and setting it on the trajectory it still follows. Voyager 2 was left to do the outer planets alone, and did, reaching Neptune in 1989. That decision is why the two spacecraft are now heading in almost opposite directions relative to the plane of the galaxy. Voyager 1 is climbing north out of it at about 35 degrees. Voyager 2 is heading south. Voyager 2 moves slightly slower, at about 15.4 kilometers per second, and its eventual near approach is to a star called Ross 248, which it will pass within about 1.7 light-years of in roughly 40,000 years. The geometry has a practical consequence on the ground. Because Voyager 2 went south, the only antenna on Earth that can send commands to it is the 70-meter dish outside Canberra. When that antenna was taken offline for 11 months of upgrades starting in March 2020, Voyager 2 could be listened to but not spoken to for the whole period. It was left running on its own, with no way to be corrected. Both spacecraft run on radioisotope thermoelectric generators fueled with plutonium-238. Each produced about 470 watts at launch. They now produce under 220. Instruments have been shut off one at a time over decades to stretch the budget, each shutdown a small permanent loss. The onboard computers hold roughly 70 kilobytes of memory between them. The original data recorder used 8-track digital tape. In November 2023, Voyager 1 began returning a repeating pattern of meaningless bits. The spacecraft was clearly alive, and clearly not saying anything. The fault was traced to a single failed memory chip in the flight data subsystem, which held part of the software the spacecraft used to package its data for transmission. The repair is the part worth holding on to. The engineering team included people who had been brought out of retirement, working from paper documentation written in the 1970s by engineers who in some cases were no longer alive. There was no way to replace the chip. The solution was to find the affected sections of code, break them into pieces small enough to fit in unused corners of the remaining memory, relocate them, and adjust every reference so the whole thing still worked. Each attempt required sending the change and waiting about 45 hours to learn whether it had helped. The first successful response came in April 2024. Full science data resumed in June. A 50-year-old computer was reprogrammed by people reading 50-year-old manuals at a distance where a single question and its answer take the better part of 2 days. The famous photograph belongs to this spacecraft too. On the 14th of February 1990, at Carl Sagan's persistent urging and over years of internal objection, Voyager 1 turned its camera back toward the inner solar system from about 6 billion kilometers and took a series of images. In one of them, Earth occupies a fraction of a single pixel, caught in a band of scattered sunlight. The cameras were shut down permanently afterwards to save power. It was the last picture either Voyager ever took. It is worth being clear about what is actually running out, because it is not the fuel. Plutonium-238 has a half-life of 87.7 years, so after nearly 5 decades, the fuel is still producing about 2/3 of its original heat. What degrades faster is the thermocouples, the devices that convert that heat into electricity. They lose efficiency steadily, and the combination of decaying fuel and decaying converters is what has taken the power from 470 watts to under 220. What happens next is a long, quiet, uneventful continuation. Power falls by roughly 4 watts a year, and the last instruments are expected to be switched off in the early 2030s. After that, the spacecraft keeps going, silent, on the same trajectory. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a small star called Gliese 445 in the constellation Camelopardalis. That is the closest it will ever come to another star, and 1.6 light-years is not close. It will then continue orbiting the center of the galaxy on a circuit taking roughly 230 million years, essentially forever, in a region where nothing is likely to touch it. And here is the thing about the farthest object we have ever made. After 5 decades of continuous flight, it is still close enough that its voice reaches us in a day. It has not yet reached the beginning of the solar system's outermost shell. It will need another 3 centuries just to arrive there. Number 13. The outer shell, nobody has ever seen. The Oort cloud is the outermost structure of the solar system, and it is the only major component of the solar system that has never been observed. Not photographed poorly, not seen faintly at low resolution, never seen by anyone, by any instrument, at any wavelength. Its inner edge is placed somewhere between 2,000 and 5,000 astronomical units from the Sun. Its outer boundary runs to somewhere between 50,000 and 100,000 astronomical units, which is between about 0.8 and 1.6 light-years. The Sun's Hill sphere, the radius inside which solar gravity still wins against the pull of the rest of the galaxy, is roughly 230,000 astronomical units, or about 0.8 light-years. Past that line, the Sun does not own anything, and anything sitting there belongs to the galaxy instead. The evidence for the whole structure is orbital. Jan Oort, working at Leiden in 1950, examined the orbits of long-period comets and noticed 2 things that a spherical reservoir explains and that nothing else explains as cleanly. The first was where the comets turn around. When the orbits were traced backward, the farthest points clustered around 20,000 astronomical units. Not scattered across every distance. Clustered. The second was the direction they arrived from. Long-period comets come at the inner solar system from everywhere, uniformly distributed across the sky, with no preference at all for the plane in which the planets orbit. A disk cannot produce that. Only a shell can. The scale is difficult to hold in the mind, because 2 facts about it seem to contradict each other, and both are true. The outer Oort cloud may contain something on the order of 1 trillion objects larger than 1 kilometer across. That is more discrete bodies than there are stars in the Milky Way. And it is also, by any standard a human being could apply, absolutely empty. Distribute 1 trillion objects through a sphere with a radius of a light-year and work out the average separation between neighbors, and the answer comes to tens of millions of kilometers. That is comparable to the distance between Earth and Mars when they are on the same side of the Sun. So stand on an Oort cloud comet. There is no other comet visible. Not dim, not distant, not there at all as far as your eyes are concerned. Overhead, the Sun is a very bright star, brighter than Venus looks from Earth, and clearly a point of light rather than a disk. It gives no useful illumination and no useful warmth. The temperature around you is a few degrees above absolute zero. And you are, technically, still inside the solar system, with the Sun still holding you in orbit, on a circuit that takes something like 1 million years to complete. Voyager 1 will reach the inner edge of this region in roughly 300 years, and will need something like 30,000 years to pass through and out the far side. 30,000 years is longer than the interval separating us from the painted caves at Chauvet. The spacecraft that has been flying for half a century has not yet reached the beginning of the last thing in the solar system. The material almost certainly did not form where it now sits. There is not enough of anything at those distances for objects to condense out of it. The prevailing account has these bodies forming much closer in the region of the giant planets, and then being flung outward by gravitational encounters with Jupiter, Saturn, Uranus and Neptune during the solar system's first 100 million years. Objects thrown outward on very elongated orbits would then have had those orbits gradually rounded and randomized by two slow influences, the gravity of stars passing at a distance and the galactic tide, which is the small difference in the Milky Way's pull across the width of the solar system. There is a further wrinkle. Because the Sun was born in a cluster of stars packed far more tightly than anything in our present neighborhood, and because every star in that cluster was flinging its own material outward at the same time, a fraction of what ended up in our Oort cloud may have been captured from other stars. Estimates for that fraction vary widely and are not well constrained, but the possibility is real. Part of the outermost shell of the solar system may not originally be ours. The idea did not begin with Oort. Ernst Öpik had proposed a distant reservoir of comets in 1932, working from similar reasoning about cometary orbits with less data to hand, which is why the structure is sometimes called the Öpik-Oort cloud. And the region is probably not uniform. Jack Hills proposed in 1981 that there is an inner, denser, more tightly bound population, closer in, perhaps 10 to 100 times denser than the outer shell, held firmly enough that passing stars cannot easily strip it. That inner region is now generally called the Hills cloud, and it may be the actual source of most of the comets that eventually reach us. There is one object we have found that may already belong to it. Sedna, discovered in 2003, has a perihelion of about 76 astronomical units and swings out to around 937 at its farthest, on an orbit taking roughly 11,400 years. Nothing in the known solar system could have put it on that path. Its perihelion is too far out for Neptune to have influenced it, and too far in for the galactic tide to explain. It is either the first inner Oort cloud object anyone has catalogued, or it is evidence of something else out there, and both readings are still argued. The rate at which the cloud delivers anything is a good measure of how thoroughly undisturbed it is. Roughly one long-period comet per year is discovered, arriving from the outer regions. 1. Out of a reservoir estimated at 1 trillion objects. That is a disturbance rate of about 1 in a trillion per year, which means the overwhelming majority of what is out there has been sitting on the same orbit, untouched, since before the Earth had a solid crust. The cloud is also the reason the outer solar system is not a stable, undisturbed place. Stars pass close enough to reach into it on a regular schedule. Gliese 710 is a small orange star, currently about 62 light-years away. It is moving almost directly toward us, and in roughly 1.3 million years, it will pass within about 10,000 astronomical units of the Sun. That is not a near miss. That is well inside the Oort cloud, closer than most of the objects in it. It will stir the region it passes through, and some of the comets it nudges will fall inward over the following millions of years. Something similar has already happened within human memory, in the loosest sense of that phrase. A small binary system known as Schultz's star passed within about 52,000 astronomical units of the Sun roughly 70,000 years ago, which is well inside the outer cloud. Modern humans were alive at the time. Some of them were looking up. The star was faint and red and would have been invisible except during flares, so nobody noticed anything, but the event happened, and it was reconstructed only in 2015 by tracing the star's motion backward. Neither of these is a threat on any timescale that matters to anyone. The comets they disturb take millions of years to arrive, and the number of them is small against the size of the solar system. What they establish is something different and more unsettling in a quiet way. The outer boundary of our solar system is not a wall. It is a region that other stars walk through periodically, and have walked through many times, and will walk through again. Beyond the Hill sphere, the Sun's grip ends, and past that boundary lies the shortest interstellar distance available from where we happen to be standing. Number 12. The nearest star there is. Proxima Centauri is 4.2465 light-years from the Sun. That is about 40 trillion kilometers. And the important fact about it is not the number, but the ranking, because Proxima is the closest star that exists. Every other star in the universe is farther away than this. There is no shorter interstellar distance available from where we are standing, and there never will be, at least not for a very long time. This is where the list changes character. Up to now, every distance has been a distance to a place we have visited, or could visit, or have at least sent something toward. Past this line, the list is about places we will look at, and not go to. The measurement has a history that took 2,000 years to resolve, and it is worth walking through, because the failure to make it was for a long time the best argument against the Earth moving at all. The idea is simple. If Earth orbits the Sun, then over 6 months our viewing position shifts by 300 million kilometers, and a nearby star should appear to shift slightly against the more distant background, then shift back. That apparent motion is called parallax, and it is exactly the effect you get by holding up a finger and closing one eye and then the other. The Greeks understood this and looked for it. They did not find it. That absence was taken, reasonably, as evidence that Earth does not move, and it was one of the strongest points in the argument against the heliocentric model for well over 1,000 years. Copernicus's answer, published in 1543, was that the stars must simply be much farther away than anyone had assumed, so far that the shift was too small to detect. He was completely correct and could not prove it. Tycho Brahe, the finest observer of his age, rejected heliocentrism partly on these grounds, because his instruments were good enough that if the stars were as close as he believed, he should have seen the shift and did not. The shift is real, and it is tiny. For the very nearest stars, it comes to under 1 second of arc, which is roughly the angular width of a small coin seen from 4 kilometers away. Anything less than the best instruments of the 1830s simply could not resolve it. It broke open in 18 months. Friedrich Bessel, using a heliometer at Königsberg, published a parallax for the star 61 Cygni in December 1838. He measured 0.314 arcseconds, which gave a distance of about 10.4 light-years. The modern figure is 11.4. It was the first time in history that anybody had measured the distance to a star. Thomas Henderson had actually got there first and did not know it. Observing from the Cape of Good Hope in 1832 and 1833, he had measured Alpha Centauri and obtained a parallax. He did not trust it. He sat on the result for years while he checked his work and finally published in January 1839, 2 months after Bessel. Wilhelm Struve announced a parallax for Vega around the same period, though with a larger uncertainty. 3 astronomers in 3 countries, working independently, ended a 2,000-year deadlock within a year and a half of each other. Proxima itself came later. In 1915, Robert Innes at the Union Observatory in Johannesburg noticed a faint red star sharing Alpha Centauri's motion across the sky. 2 years later, its parallax was measured, and it proved to be very slightly closer than Alpha Centauri itself, making it the nearest known star to the Sun. That is a title it has held for over a century. Proxima is not impressive to look at, which is part of why it took so long to notice. It is a red dwarf with about 12% of the Sun's mass and 14% of its radius. It radiates roughly 1/2000th of the Sun's light. Despite being the nearest star to us by a comfortable margin, it has never been visible to the naked eye, and never will be. It orbits the bright pair Alpha Centauri A and B at a distance of about 13,000 astronomical units, on a circuit taking around 550,000 years. The precision we now have on this distance is worth stating, because it is the sharpest number on this entire list. The Gaia spacecraft, operating from a point 1.5 million kilometers from Earth and spinning slowly while it repeatedly measures the positions of stars against each other, has fixed Proxima's parallax at 768.5 milliarcseconds, with an uncertainty of a fraction of a microarcsecond. Translated into something physical, that is a level of angular precision comparable to measuring the width of a human hair from 1,000 kilometers away. Gaia has done the same for nearly 2 billion stars. The system Proxima belongs to is worth a moment as well. Alpha Centauri A is a near twin of the Sun, slightly larger and slightly brighter. Alpha Centauri B is a cooler orange dwarf. The two orbit each other every 79.9 years at a separation that varies between about 11 and 36 astronomical units, so their mutual distance ranges from roughly Saturn's orbit to well beyond Neptune's. Together they form the 3rd brightest point of light in the night sky, though only from the southern hemisphere. Proxima hangs off the system at 400 times that separation, barely holding on. Now the part of this entry that actually matters, which is what 4.2 light-years does to every method of travel we have. Voyager 1 moves at 17 kilometers per second. If it were pointed at Proxima, which it is not, it would take about 73,000 years. 73,000 years ago, modern humans had not yet reached Europe. Parker Solar Probe reached 192 kilometers per second, but only at the bottom of the Sun's gravity well, and it cannot keep that speed once it climbs back out. Even pretending it could, the trip would take around 6,600 years. That is longer than the interval separating us from the first written language. The problem is not engineering refinement. Chemical rockets are not slow at this task, in the way that a bicycle is slow compared to a car. They are the wrong category of answer entirely. Getting a meaningful payload to Proxima in a human lifetime using chemical propulsion would require a quantity of fuel with no relationship to anything that could be built. Breakthrough Starshot, announced on the 12th of April 2016, is the only serious proposal that puts the answer inside a working career, and it gets there by abandoning the idea of a spacecraft as an object. The concept is a gram-scale chip containing a camera, a power source, and a transmitter attached to a sail about 4 meters across and a few hundred atoms thick. A ground-based laser array delivering something like 100 gigawatts pushes on that sail for a few minutes, which is enough to accelerate something that light to about 20% of the speed of light. Transit time, roughly 20 years. Then another 4.24 years for the pictures to come home. None of the hard problems has been solved. The sail material has to survive a laser intense enough to accelerate it without absorbing enough energy to vaporize. At 20% of light speed, a single grain of interstellar dust arrives with the energy of a small explosion, and the interstellar medium is not perfectly clean. Aiming a beam at a 4-meter target that is already moving is not trivial. And the deepest problem is the last one: how a gram-scale transmitter, powered by whatever a chip can carry, sends anything detectable across 4 light-years to a receiver here. It remains, nonetheless, the only concept in existence where the answer arrives while the people who launched it are still alive to read it. There is one more thing about Proxima that reframes the whole entry. It is a slow burner. Red dwarfs of its mass fuse hydrogen so gradually and circulate their interiors so thoroughly that they can keep going for something like 4 trillion years. The current age of the universe is 13.8 billion. Proxima has a projected lifetime roughly 300 times longer than everything that has already happened. The Sun will be a white dwarf, cooling toward invisibility, and Proxima will not yet have reached the early middle of its life. There is at least something worth arriving at. Proxima Centauri b, confirmed in August 2016, has a minimum mass of about 1.07 Earths and completes an orbit every 11.2 days, inside what would conventionally be called the habitable zone. There may be more than one. A second planet, Proxima c, on an orbit of about 5 years, has been reported and partially supported. A candidate sub-Earth, Proxima d, on a 5-day orbit, has also been announced. Neither is as securely established as Proxima b, and both sit at the edge of what current instruments can separate from the star's own activity. The difficulty is the star. Proxima is a flare star, and in March 2016, an event was recorded that brightened it by a factor of 68 in the ultraviolet over the course of seconds. Whether any atmosphere can survive repeated exposure of that kind on a planet orbiting 11 days out is unresolved and may stay unresolved until something goes and looks. Which is the whole problem this entry is about. Number 11. The space between stars. In the Sun's neighborhood, the typical separation between one star and its nearest neighbor is about 5 light-years. The Sun's diameter is 1.39 million kilometers. 5 light-years is about 47 trillion kilometers. Divide one into the other, and you get a ratio of roughly 34 million to 1. That ratio is the single most useful number in this entire subject, and almost nobody carries it around. Here is what it means physically. Shrink the Sun until it is a grain of sand 1 millimeter across. At that scale, the nearest other grain of sand sits 34 kilometers away. Not 34 meters. 34 kilometers, with absolutely nothing in between except a thin haze of hydrogen atoms so sparse it would take a cubic meter to collect 100,000 of them. Now, scatter those grains through the galaxy at that density, in their hundreds of billions, and you have the Milky Way at true scale. Every photograph of a galaxy, every rendering, every illustration shows a bright, continuous glow. That glow is real, and it is produced by objects separated from each other by 34 million times their own width. This one ratio explains something that otherwise sounds like it cannot possibly be right. Galaxies collide. They do it routinely, all over the universe, and our own galaxy will do it. The Milky Way and Andromeda will begin interacting in something like 4 to 4.5 billion years. During that encounter, the expected number of direct collisions between individual stars is, to a very good approximation, 0. 2 objects containing 1 trillion stars between them will pass through one another. They will tear each other apart gravitationally. They will fling long streams of stars out into intergalactic space. They will pass, separate, fall back, and merge over roughly 1 billion years into a single galaxy that looks nothing like either of its parents. And through the entire process, the probability that any one star physically strikes another star is negligible. A galaxy collision is not a collision of stars. It is a collision of gas clouds and dark matter halos, with the stars falling through the gaps in the dark. The gas is where the actual physics happens, and this is the part that makes the pictures. Interstellar clouds cannot pass through each other. They are enormously less dense than anything on Earth, but they are dense enough that when two of them meet at hundreds of kilometers per second, they shock, compress, and heat. Compressed gas collapses. Collapsing gas forms stars. This is why merging galaxies light up so dramatically. The antennae galaxies, about 45 million light-years away and partway through a merger that began several hundred million years ago, contain thousands of young superstar clusters, each holding hundreds of thousands of stars, all formed in the compression fronts of the encounter. The visible drama of a galaxy merger is a gas phenomenon from beginning to end. The stars are bystanders, too far apart to take part in it. There is a detail about the Andromeda encounter that is worth stating carefully, because it is genuinely uncertain and often reported as though it were settled. Andromeda's motion toward us along our line of sight is well measured at about 110 kilometers per second. Its sideways motion is not. Measuring the sideways drift of a galaxy 2.5 million light-years away means detecting a shift of a few tens of microarc seconds over years of observation, and that is at the very limit of what any instrument can do. Whether the two galaxies strike each other centrally or pass at a distance and take much longer to settle depends entirely on that number, and improved data has moved the answer back and forth more than once. The local density of stars gives another way to hold the emptiness. There are about 4/1000ths of a star per cubic light-year in this part of the galaxy, which is one star for every 250 cubic light-years of space. Within 10 light-years of the Sun, there are roughly a dozen star systems. Within 20, about 100. Expand the sphere by a factor of 2, and the count rises by a factor of 8, because the volume grows as the cube, and the sky is still overwhelmingly empty at every radius. There is one environment where the ratio changes enough to matter. Globular clusters are ancient, tightly packed balls of 100,000 to 1,000,000 stars, and in their cores, the density reaches hundreds to thousands of stars per cubic parsec. That is around 1,000,000 times the local density. Separations there shrink from light-years to something closer to light-weeks, and at that density, close encounters and outright collisions do occur. The signature is a population of stars called blue stragglers, which appear hotter and younger than the cluster they live in. A globular cluster formed all its stars at once, 12 billion years ago, so any star still burning bright and blue should have exhausted itself long ago. Blue stragglers exist because they are not what they seem. They either pulled material off a companion or merged with one outright, gaining enough mass to restart as something more massive and hotter. They are stars assembled from the wreckage of other stars, and they only exist where the spacing is tight enough for stars to meet. Even there, though, the sky would not look the way people imagine. Stand on a hypothetical world inside the core of a cluster like 47 Tucanae. You would see something remarkable. Perhaps a few thousand stars brighter than Venus appears from Earth, filling the sky with the total illumination somewhere between a full moon and the last stage of twilight. It would be genuinely spectacular and nothing like daylight, and the sky would still be mostly black between the points of light. Collisions in those cores are estimated at roughly 1 per 10,000 years per cluster. By any human measure, that is essentially never. Across the 12 billion year life of a globular cluster, it is more than 1,000,000 events, which is why the blue stragglers are there in numbers. The last consequence of this ratio is the one that closes the previous entry's argument. Between here and Proxima Centauri, there is nothing. No station, no waypoint, No convenient body to refuel at, no rock large enough to be worth stopping for, no gravitational assist available from anything. The interstellar medium in this region of the galaxy holds roughly 1/10 of a hydrogen atom per cubic centimeter. That is about 10 million times thinner than the best vacuum a laboratory on Earth can produce. An interstellar journey is not a voyage along a corridor with features in it. It is 4 light-years of nothing at all, with a star at either end. And that same emptiness has one enormous compensation, which is that light crosses it without being interfered with. Nothing scatters it. Nothing absorbs it. A photon leaving a star's surface travels for years, or millennia, or billions of years, and arrives carrying essentially the same information it left with. One last consequence of the spacing is worth mentioning, because it concerns our own history. Over 4.5 billion years, the Sun has almost certainly passed through several of the galaxy's spiral arms, which are regions where the density of gas and young stars is higher than average. Passing through one should, in principle, raise the local rate of supernovae and increase the flux of cosmic rays reaching the solar system. People have looked for the signature of those passages in the geological record for decades. Nothing convincing has ever been isolated. The arms are real, the passages happened, and even at those higher densities, the spacing between stars remained large enough that our star crossed them without leaving a mark anyone can find. Which means the sky overhead is not a place. It is a set of depths, stacked on top of each other, and every point of light in it is showing a different century. Number 10. The depth of the night sky. On a genuinely dark night, away from towns, a person with good eyesight can see roughly 3,000 stars at once. It looks like a single scene. It is not a scene at all. It is a composite, assembled by geometry out of a range of dates spanning most of recorded history, and no 2 points in it are showing the same moment. The stars visible to the unaided eye are not arranged on a shell. They sit at every distance from a few light years to several thousand, and the reason they all look roughly comparable in brightness is that the nearby ones are mostly faint and the distant ones are mostly enormous. A star's apparent brightness is a product of what it actually puts out and how far away it is, and those 2 factors happen to compensate for each other well enough to produce the flat-looking sky we grew up with. Some specific numbers make this concrete. Sirius is 8.6 light-years away, which means its light is about as old as a child starting secondary school. Vega, at 25 light-years, is showing a scene from the middle of the last decade. Arcturus sits at 37 light-years, so its light left during the 1980s. Polaris, the pole star, is at about 447 light-years, which means the star people have navigated by for centuries is displaying light that departed before the telescope had been invented. Deneb is the sharpest case. It is one of the brightest stars in the northern sky, a corner of the summer triangle, and it sits somewhere around 2,600 light-years away. Its light left during the early Iron Age. For it to still appear that bright from here, after crossing that distance, it has to be putting out something on the order of 200,000 times the Sun's output. It is not a nearby star that happens to be bright. It is an enormously luminous object very far away, and every time anyone has looked at it, they have been looking at the Iron Age. Betelgeuse is the useful entry here, because it is close enough to matter and far enough to be genuinely uncertain. Estimates put it between about 400 and 650 light-years, with figures near 550 appearing most often. That range is not carelessness. Betelgeuse is a red supergiant roughly 700 times the Sun's diameter, and its surface is not a smooth sphere. It boils in convection cells the size of Earth's orbit, which means the center of light of the star physically shifts as different regions rise and sink. Parallax works by measuring a tiny shift in position over 6 months. Measuring a tiny shift in the position of a target that is itself wobbling is a hard problem, and it is why one of the nearest supergiants has a distance known to about 20%, while far fainter and better-behaved stars are known to a fraction of a percent. Between October 2019 and February 2020, Betelgeuse faded. It dropped to about 40% of its normal brightness, which is the deepest dimming ever recorded for it, and was easily visible to anyone who knew the constellation. Orion looked wrong. The speculation was immediate and predictable. The answer arrived in 2021, and it was more interesting than the guess. Direct imaging showed the star had ejected a large quantity of material from its southern hemisphere, a bubble of gas that moved outward, cooled, and condensed into dust. That dust sat between us and part of the star's surface and blocked it. Betelgeuse had not begun anything. It had thrown off a piece of itself, and for the first time anyone had watched a supergiant do it in enough detail to reconstruct the sequence. The distance produces one genuine strangeness here, and it is worth stating precisely rather than dramatically. Betelgeuse will end as a supernova. Its remaining lifetime is estimated in the region of 100,000 years, which on the timescale of a star is very close to the end, and on the timescale of a person is not close to anything. Because the light takes roughly 550 years to reach us, there is a sentence people reach for, which is that it might already have exploded and we would not know. That sentence is technically true. It is also nearly empty, because the probability that the event happened to fall inside the specific 550-year window currently in transit is somewhere around 0.5%. When it does happen, we will get a small amount of notice. Neutrinos escape a collapsing stellar core almost immediately, while the light has to fight its way out through the star's envelope. The detectors would register the neutrino burst hours before anything appeared in the sky, which is enough time for observatories worldwide to be pointed at the right place before the light arrives. There is precedent for exactly that sequence, and it happened within living memory, though not with a star anyone could name. We will come to it in 2 entries' time. It is worth noting how much of this sky most people have already lost. The faintest stars a dark adapted eye can register sit around magnitude 6.5. Light pollution in a large city typically pushes the limit to magnitude 3 or worse, which removes roughly 95% of the visible stars. In a heavily lit urban center, a person might see 200 stars on a clear night instead of 3,000, and almost all of the remaining 200 are the nearby, ordinary ones. The most distant part of the naked eye sky, the Denebs and the Eta Carinae, is the part that disappears first. There are further examples in the same sky. Eta Carinae, at about 7,500 light-years, brightened in 1843 until it was the second brightest star in the sky, threw off around 10 solar masses of material, and then survived. Nobody has fully explained what happened, and the light from that event had already been traveling for 75 centuries when it reached the observers who recorded it. Rigel, in the same constellation as Betelgeuse, sits at roughly 860 light-years and outputs about 120,000 times what the Sun does. If Rigel were placed where Sirius is, it would cast shadows at night. And beyond all the stars, there is one more thing the naked eye can reach, though only from a properly dark sight with properly dark adapted eyes. It is not a star. It is the entry we will come to 2 steps from now, and the light it is sending us is 2.5 million years old. The instruments that fixed most of these numbers deserve a note. The Gaia spacecraft has measured parallaxes for nearly 2 billion stars, which is more than 1% of the galaxy, and for well-behaved stars, the precision is extraordinary. But the errors do not scale with brightness in the way intuition suggests. The very brightest stars saturate the detectors and need special handling, and the physically largest ones have surfaces that move. Some of the most famous stars in the sky are among the worst measured objects in the catalogue, and Betelgeuse is the standing example. That is the point of this entry. There is no such thing as looking at the sky as it is. Every night sky any human being has ever seen was already an archive, and the only reason it looks like a single instant is that we are not equipped to notice the difference. But the stars a person can name are only the nearest fringe of the structure they belong to. Past them, in the direction of Sagittarius, is the center of the galaxy itself. Number 9. The center of our own galaxy. The center of the Milky Way lies about 26,000 light-years from the Sun, in the direction of the constellation Sagittarius. The best current figure comes from tracking the orbit of a single star around the object at the center, and it gives 8,178 parsecs with an uncertainty of 13. Converted, that is 26,673 light-years, known to better than 1/5 of 1%. That precision is very recent, and for most of the history of astronomy, nobody even knew which direction to look. William Herschel attempted to map the shape of the galaxy in the 1780s by counting stars in different directions and assuming that more stars meant more depth. His map put the Sun close to the middle. The conclusion was wrong, and the reason it was wrong is the reason this entry is difficult. Interstellar dust dims and reddens starlight, and it does so roughly equally in every direction along the plane of the galaxy, which means the view cuts off at about the same distance, no matter where you look. Any observer inside a dusty disk, anywhere in it, appears to be at the center. The dust manufactures the illusion of centrality for everyone. The correction came from Harlow Shapley in 1918. Rather than counting stars in the disk, he studied globular clusters, which sit above and below the plane where the dust is thinner. He used variable stars inside them to estimate their distances and then plotted where they were. They were not distributed around the Sun. They were distributed around a point tens of thousands of light-years away, in Sagittarius. In one piece of work, the solar system was moved from the middle of the galaxy to a position out in the suburbs, and nothing since has moved it back. The dust that fooled Herschel has not gone anywhere. In visible light, the galactic center is completely invisible. The extinction along that line of sight amounts to about 30 magnitudes, which means roughly 1 photon in a trillion gets through. Everything known about the region has been assembled at wavelengths that pass through dust, infrared, radio, and X-ray. Optical astronomy has never seen the center of its own galaxy, and never will. What sits there is a black hole of about 4.3 million solar masses, designated Sagittarius A star, packed into a region smaller than the orbit of Mercury. The evidence for it is the most direct available for any black hole anywhere, and it took 3 decades to assemble. 2 independent teams, one led from Germany using telescopes in Chile and one led from California using telescopes in Hawaii, tracked individual stars orbiting the center year after year through the infrared. Not statistical measurements of a crowd. Individual named stars, plotted around a closed path. The best of them is called S2. It completes an orbit every 16.05 years, which is short enough that the astronomers involved have now watched it go around more than once. At its closest approach, it comes within about 120 astronomical units of the center and moves at nearly 3% of the speed of light. Reinhard Genzel and Andrea Ghez shared the 2020 Nobel Prize in Physics for that work, and what earned it was not a single discovery, but 27 years of returning to the same patch of sky and measuring the same stars again. S2's orbit has since done something else useful. It does not close. Each time round, the point of closest approach shifts slightly forward, which is precisely the effect general relativity predicts and which was first detected in Mercury's orbit around the Sun. At Sagittarius A star, the effect is about 1 million times larger, and it has been measured. S2 is not even the fastest thing in that neighborhood. A star catalogued as S4714 has been clocked at about 8% of the speed of light at its closest approach, which makes it the fastest star known anywhere. It comes within roughly 12 astronomical units of the black hole, closer than Saturn is to the Sun, and survives the pass. The presence of those stars is itself an unsolved problem. Within a parsec of Sagittarius A star, there is a dense population of young, massive, hot stars, and they should not be able to form there. The tidal forces from the black hole ought to tear apart any gas cloud trying to collapse long before it becomes a star. Either the stars formed elsewhere and migrated inward as a cluster, which has difficulties of its own, or gas can collapse under conditions nobody has properly modeled. The question is still open. The image released on the 12th of May, 2022, required a telescope the size of the planet. The Event Horizon Telescope is not one instrument. It is 8 radio observatories, from Hawaii to Chile to Spain to the South Pole, all observing the same target at the same time and recording the raw signal alongside an atomic clock. Combined afterwards, they act as a single dish with a diameter equal to the spacing between them. The data volumes made network transmission impossible, so the recordings were written to hard drives and physically flown to processing centers in Massachusetts and Germany. The drives from the South Pole could not be shipped until the Antarctic season allowed aircraft, which added months to the schedule. The observations were taken in April 2017. The image came out 5 years later. The delay was not bureaucracy. Sagittarius A star is small enough that material orbiting it completes a circuit in minutes rather than days, which means the source changes appreciably during a single night's observation. Reconstructing a still image from a subject that will not hold still required techniques that had to be built for the purpose. Sagittarius A star is remarkably quiet for what it is. It swallows perhaps 100 millionth of a solar mass per year and radiates far below the theoretical maximum for an object of its size. Compared with the monstrous, blazing centers of some other galaxies, ours is essentially dormant. It has not always been. Enormous lobes of gamma-ray and X-ray emission extend above and below the galactic plane, reaching about 25,000 light-years in each direction. They were mapped in gamma rays in 2010 and in X-rays at even greater extent in 2020. The most natural reading is that they record an outburst from the galactic center a few million years ago, when something substantial fell in. There is other structure there that nobody expected and nobody has explained. Radio imaging with the Meerkat array in South Africa has revealed roughly 1,000 magnetized filaments threading the region around the galactic center. Each is tens of light-years long, remarkably straight, often arranged in parallel groups, and glowing from electrons spiraling along magnetic field lines. They appear to have formed within the last few million years. What organizes them into those shapes and what supplies the energy is unknown. And there is evidence for activity far more recent than that. Molecular clouds scattered around the central region are glowing in X-rays in a pattern that does not match anything currently illuminating them. The best explanation is that they are reflecting a flash that has already passed, and working backward from their positions puts the flash within the last few hundred years. If that reading holds, the black hole at the center of our galaxy flared while human beings were already writing things down, and the light from it has been bouncing off nearby gas ever since. All of this is being observed at a remove of 26,600 years. The image released in 2022 shows the center of our galaxy as it was when the last ice age was near its coldest and the mammoths were still walking. There is a way to make that particular number land. The Sun travels around the galactic center at about 230 kilometers per second, and one full circuit takes something over 200 million years. The light in that photograph left before the Sun had completed even 1/100th of its current lap. In the time it took the image to reach us, the solar system moved about 1,000th of the way around its own orbit, and that small arc contains the whole of human history. And the center is not even the far side. It is roughly 1/4 of the way across the structure we are looking at. Number 8. Crossing the galaxy. The stellar disk of the Milky Way is about 100,000 light-years across. Some measurements of its outer structure, including faint streams of stars that clearly belong to it, push that figure toward 150,000 or beyond. Light needs 1,000 centuries to cross it once, and light is not merely the fastest thing we have. It is the fastest thing there is, and nothing with mass will ever match it. A signal sent from one rim of the galaxy to the other would depart while the sender's species was working out how to plant seeds deliberately, and arrive long after every record of the sender had eroded away. Within one galaxy, within the single structure our star belongs to, the disk is also far thinner than any picture conveys. The thin disk, where most of the young stars and almost all of the gas live, is about 1,000 light-years top to bottom. That is 1/100th of its width. Take a dinner plate and imagine the galaxy printed on it at that proportion, and the thickness would be about 2 sheets of paper. Almost everything interesting is in that sheet. Almost all of the volume is above and below it, where there is very little except old stars, globular clusters, and dark matter. The Sun is not sitting still in this arrangement. It orbits the galactic center at about 230 kilometers per second. That is 828,000 kilometers per hour, which is fast enough to cross the Earth-Moon gap in under half an hour. At that speed, the solar system covers roughly 20 kilometers in the time it takes to read a short sentence aloud. And a full circuit at that speed takes somewhere between 225 and 250 million years. That interval is called a galactic year. The Sun has completed about 20 of them. 20 is a small enough number to hold, and it is the reason this entry works. Everything in the history of this planet fits inside 20 laps. The last time the solar system occupied this position in its orbit, roughly 230 million years ago, the Permian extinction had recently finished killing off the great majority of species on Earth. The continents were assembled into the single mass of Pangaea. The first dinosaurs were appearing, small and unremarkable, and would not become dominant for another 20 million years. There were no flowers anywhere on the planet. There were no birds and no mammals worth mentioning. 2 galactic years ago, complex life on land essentially did not exist. 4 galactic years ago, there were no animals of any kind, and the oceans held nothing more complicated than single cells and mats. Run it forward instead. The Sun's total main sequence lifetime is around 10 billion years, which is about 50 galactic years. It is roughly 20 into that. Everything that has ever lived on this planet has done so during a span covering less than half of one star's single orbital history. The orbit itself is not a clean circle traced in a flat plane. The Sun oscillates vertically, rising perhaps 300 light-years above the galactic plane and sinking the same distance below on a cycle of 60 to 70 million years. Since the 1980s, people have repeatedly proposed that this bobbing motion should correlate with periodic mass extinctions, on the reasoning that passing through the dense plane increases exposure to whatever is dangerous out there. The proposal keeps returning and keeps failing. The statistics do not support a clean periodicity, and the physical mechanism has never been demonstrated. The motion is real and well measured. The consequences are not established, and it is worth being honest about that, rather than repeating the attractive version. There is genuine uncertainty about how many stars are in the thing we are crossing. The usual figure is between 100 and 400 billion, and that is a very wide range for a quantity that sounds like it ought to be countable. The uncertainty comes almost entirely from red dwarfs. They are the most common type of star by a large margin. They are intrinsically faint, and beyond a few thousand light-years, they are essentially invisible to us. The total, therefore, depends on how many faint stars you assume are hiding behind the ones you can see, and different assumptions give answers that differ by a factor of 4. The disk is also not where the mass is. Beyond the visible stars lies a stellar halo of ancient, metal-poor stars reaching far above and below the plane, and beyond that a dark matter halo that may extend 1,000,000 light-years in every direction. At that radius, our galaxy's halo and Andromeda's are already overlapping. The two galaxies, in the sense that matters gravitationally, are already touching. The galaxy is also not the tidy pinwheel of the illustrations. There is a central bar of stars roughly 25,000 light-years long, running through the core, which was suspected for decades and only confirmed properly by infrared surveys in the early 2000s. The outer disk is visibly warped, bent upward on one side and downward on the other, like the brim of a hat, most likely under the gravitational influence of the Large Magellanic Cloud. And in 2018, the Gaia mission found something nobody had predicted. Plotting the vertical positions and vertical velocities of millions of nearby stars produced a spiral pattern, a shape that looks like a snail shell when drawn out. That pattern is the signature of a disturbance. The disk was disturbed at some point between 300 and 900 million years ago, most likely by a satellite galaxy passing through it, and the stars are still oscillating in a coherent pattern from the impulse. The galaxy is ringing, and we are inside the bell. The disk also carries the wreckage of things it has eaten. Around 2018, astronomers identified a population of halo stars sharing a distinctive set of orbits, all moving in the same peculiar way. The interpretation is that they came from a single dwarf galaxy, now called Gaia Enceladus, which merged with the Milky Way roughly 10 billion years ago. Something like a quarter of the stars in the galaxy's halo are its remains. The Sagittarius dwarf galaxy is currently going through the same process, being pulled into a long stream that wraps most of the way around the sky, and it has already passed through the disk at least twice. The spiral arms themselves are not what they appear to be either. They are not fixed structures made of the same stars going round together, because if they were, the differential rotation of the disk would have wound them into a tight coil within a few orbits, and they have plainly not done that. The resolution, proposed in the 1960s, is that the arms are density waves. They are regions where the orbits of stars bunch up temporarily, and material passes through them the way cars pass through a traffic jam that itself moves slowly along the road. Gas entering an arm gets compressed and forms bright new stars, which is why the arms glow, and the stars leave the arm again a few tens of millions of years later. There is a last piece to this entry, and it is that nothing here is stationary in any sense. The Sun carries the solar system around the galaxy at 230 kilometers per second. The galaxy itself is falling toward the center of mass of the local group. The local group as a whole is moving toward the great attractor at roughly 600 kilometers per second. Add all the motions together and measure them against the cosmic microwave background, which is the closest thing to a fixed reference the universe offers, and the total comes to about 370 kilometers per second. Not one location mentioned anywhere on this list has stayed where it was during the sentence that described it. Step outside the disk entirely, look south, and the next thing out there has been visible to the naked eye for as long as there have been eyes in the southern hemisphere to see it. Number 7. 168,000 light-years. The Large Magellanic Cloud sits about 163,000 light-years away. The Small Magellanic Cloud is at about 200,000. From the southern hemisphere, they are visible to the naked eye as two detached patches of the Milky Way, faint and slightly fuzzy, sitting apart from everything else. They have been known for as long as there have been people in the southern sky. Aboriginal Australian traditions record them. Polynesian navigators used them. Persian astronomers described them in the 10th century from latitudes far enough south to see them. Europeans wrote them down when Antonio Pigafetta, sailing with Magellan's expedition in 1519, noted them in his journal and the name attached to Magellan and stayed. These are the first entries on this list that are separate galaxies. The Large Magellanic Cloud holds something like 30 billion stars across a span of about 32,000 light-years, which makes it a substantial object in its own right rather than a fragment. Measurements of its motion through the 2010s indicate it is moving fast enough that it may be on its first pass rather than in a long settled orbit, and its mass may be over 1/10 of the Milky Way's, which is large enough that it is measurably bending our galaxy's disk out of shape. Now, the reason this entry sits where it does on the list. On the 23rd of February 1987, at 35 minutes past 7 in the morning Universal Time, 3 detectors buried under 3 different mountains recorded something almost nobody was watching for. The Kamiokande detector in a Japanese zinc mine registered 11 neutrino events over 13 seconds. The Irvine, Michigan Brookhaven detector in an Ohio salt mine registered 8. The Baksan Observatory under the Caucasus registered 5. 24 particles in 13 seconds from a source 168,000 light-years away. Picture what that looked like where it happened, because it looked like almost nothing at all. Kamiokande is 3,000 tons of purified water sitting in a stainless tank a kilometer underground, lined with photomultiplier tubes staring inward at total darkness. Neutrinos pass through the Earth as though the planet were not present, and once in a great while, one strikes an electron hard enough to send it through the water faster than light travels in water, which produces a faint blue cone of Cherenkov radiation. That is what the tubes are watching for. On that morning, 11 cones flared and faded inside 13 seconds. Nobody was in the room. Nobody was in the mountain. The signals went into a data tape and sat there. The star that sent them had already been dead for 168,000 years and had died before there was any such thing as a human being. About 3 hours later and 11,000 kilometers away, Ian Shelton, a resident observer at Las Campanas in Chile, pulled a photographic plate of the Large Magellanic Cloud out of the developer and saw a star that had not been on the previous night's plate. He carried it outside. He looked up. And it was there, plainly visible to his eyes, a new point of light in a place that had not had one. Supernova 1987A was the first supernova visible without instruments since 1604. It remains the only object in the sky, other than the Sun, from which neutrinos have ever been detected. The 3-hour gap between the particles and the light is not an accident of timing. It is the entire physics of the event, and theory had predicted it in advance. When the core of a massive star collapses, about 99% of the energy released leaves as neutrinos. Neutrinos barely interact with matter, so they stream out of the collapsing core almost immediately, at essentially the speed of light. The light has no such freedom. The photons produced in the collapse have to fight their way outward through the entire remaining body of the star, scattering constantly, and that takes hours. So the neutrinos left first, and they held their lead for 168,000 years. A lead of 3 hours over that journey is a margin of about 1 part in 50 million after crossing 1.6 quintillion kilometers. And the observed margin matched the prediction. The numbers on the detection deserve a moment. Something on the order of 10 to the 58th neutrinos were released by that star. Roughly 100,000 trillion of them passed through each of those detectors. 24 were caught. Every human being alive on the 23rd of February 1987 had several 100 trillion neutrinos from that star pass through their body during those 13 seconds. Nobody felt anything, because that is what neutrinos do, and it is the reason the detectors have to be that large and that far underground, and that patient. The star that exploded had already been catalogued. It carried the designation Sandulique -69 202, and it was a blue supergiant. This was a genuine problem, because theory at the time held that supernovae of that type came from red supergiants, and reconciling the observation with the models took years of work. The current understanding involves the star having been part of a binary that merged, which would explain both the color and the peculiar triple-ring structure of gas surrounding the remnant. That structure has been putting on a slow display ever since. Around 2001, the expanding shock wave from the explosion began hitting a ring of material the star had shed thousands of years before it died, and the ring lit up in a string of hotspots that brightened one after another over the following 2 decades. It has been photographed the whole way through. There was one thing missing for a very long time. A core collapse of that kind should leave a neutron star behind, and for 35 years, nobody could find it. The remnant is thick with dust, and the object, if it is there, is buried. Only in 2024 did infrared observations produce evidence consistent with a neutron star sitting inside the debris, exactly where it was supposed to be all along, and simply obscured. There is one region of the Large Magellanic Cloud worth naming on its own. The Tarantula Nebula is the most active star-forming region anywhere in the local group, and it produces stars on a scale the Milky Way simply does not manage anywhere. At its heart sits a cluster containing R136A1, which at roughly 200 solar masses is the most massive star known. If the Tarantula Nebula were placed where the Orion Nebula is, at about 1,300 light-years, it would cover a quarter of the sky and cast shadows on the ground at night. The clouds have also left a trail. A long ribbon of hydrogen gas called the Magellanic Stream wraps more than 100 degrees across the sky, stripped out of the 2 galaxies by their passage through the Milky Way's halo. Radio telescopes mapped it long before anyone had settled where it came from. It is a visible record of 2 objects being slowly pulled apart, written in a gas that emits at a single radio wavelength and nothing else. Both clouds are also chemically primitive compared with our galaxy. They contain a smaller proportion of elements heavier than helium, which makes them the nearest available approximation to the conditions in which the early universe formed its first generations of stars. A great deal of what we understand about star formation in the young universe has been worked out by studying 2 objects that Southern Hemisphere observers can see with their eyes on any clear night. Neutrino astronomy as a working field effectively began with those 24 events, and the recognition followed. Warning networks now exist, specifically because of what happened that morning, so that when the next nearby star collapses, the neutrinos will trigger an alert, and the telescopes will already be pointed at the right patch of sky before the light arrives. There is one more thing about the Large Magellanic Cloud that belongs to this list rather than to any other. Current models suggest it will merge with the Milky Way in roughly 2.4 billion years, well before Andromeda arrives. The object that southern observers have watched for tens of thousands of years, and that delivered the only stellar message ever received by something other than a telescope, is on its way in. The next entry is farther still. It is also the last thing on this list a person can see with nothing but their own eyes. Number 6, 2.5 million light-years. The Andromeda Galaxy is about 2.5 million light-years from here, and it is the most distant object a human being can see without any instrument at all. On a dark night, in the constellation that carries its name, it appears as a faint, elongated smudge that most people walk past without noticing. Its full extent, most of which is too dim for the eye to register, covers about 3 degrees of sky. That is 6 times the width of the full moon. The light arriving tonight left before the genus Homo existed. For almost the whole history of astronomy, nobody knew what it was. Abd al-Rahman al-Sufi described it around the year 964 as a small cloud. Charles Messier catalogued it in 1764 as the 31st entry in his list of objects that were not comets and should therefore be ignored by comet hunters. It sat in the catalogues as a nebula, which simply meant a fuzzy patch, and the assumption was that fuzzy patches were clouds of gas somewhere inside our own galaxy. There was an alternative on the table, and it had been there for a long time without any evidence behind it. Immanuel Kant, writing in 1755, suggested that some of these patches might be entire star systems comparable to the Milky Way, seen from enormous distances. He called them island universes. It was a good guess, and it stayed a guess for 170 years. The argument came to a head on the 26th of April 1920 in a hall at the Smithsonian Museum of Natural History in Washington. It is remembered as the Great Debate. Harlow Shapley took one side. He had just done the work that correctly moved the Sun out of the center of the galaxy, and he argued that the Milky Way was enormous, far larger than anyone had assumed, and that the spiral nebulae were relatively nearby objects inside it. Heber Curtis took the other side. He argued that the Milky Way was smaller than Shapley claimed, and that the spiral nebulae were separate galaxies at very great distances. Both men had real evidence. Both were partly right and partly wrong. Shapley's galaxy size was closer to correct than Curtis's. Curtis's reading of the nebulae was correct, and Shapley's was not. The debate settled nothing on the night because neither of them possessed the measurement that would decide it. That measurement was made 3 years later. Picture Mount Wilson on the night of the 5th into the 6th of October, 1923. The dome is cold. The 100-inch Hooker telescope, the largest in the world, is tracking the outer region of the Andromeda Nebula on a glass photographic plate. Edwin Hubble is looking for novae, stars that flare briefly and fade, because counting them gives a rough handle on distance. He finds 3 candidates and marks each one with the letter N in the emulsion border. Then he compares the plate against earlier exposures of the same field. 2 of the 3 behave as novae should. The third does not. It brightens and dims and brightens again on a regular cycle. It is not a nova at all. It is a Cepheid variable, and Cepheids have a property discovered by Henrietta Swan Leavitt at Harvard 15 years earlier. The period of their pulsation is tied directly to their true brightness. Measure the period, and you know how much light the star is actually producing. Compare that with how bright it looks, and you have the distance. Hubble crosses out the N. Beside it, in red ink, he writes VAR with an exclamation mark. The plate is catalogued H335H, and it still exists. The distance he calculated was about 900,000 light-years. That figure was too small because the calibration of Cepheids was not yet properly understood and would be corrected upward over the following decades. But it did not matter that it was too small. It was far enough. 900,000 light-years put the object well outside any plausible boundary of the Milky Way, and the question was closed. In one night, the known universe went from being one galaxy to being an unknown number of them. Hubble wrote to Shapley in February 1924 with the result. Shapley, reading the letter, is reported to have said that this was the letter that destroyed his universe. The person whose work made that night possible was not on the mountain and never got to use a telescope of her own. Henrietta Swan Leavitt was employed at the Harvard College Observatory as a computer, which at the time meant a woman paid a low hourly wage to examine photographic plates and record what was on them. She was assigned the variable stars in the Magellanic Clouds. Because all the stars in a given cloud sit at essentially the same distance, their apparent brightnesses could be compared directly, and Leavitt noticed that the brighter ones took longer to cycle. She published the relation in 1908 and refined it in 1912. She was not permitted to pursue the implications. She died in 1921, 2 years before Hubble used her relation on that plate, and 4 years before it settled the size of the universe. The relation itself is worth understanding, because most of the rest of this list depends on it. A Cepheid variable pulses because its outer layers cycle between two states of ionization, trapping and releasing heat like a valve. The physics of that cycle depends on the star's mass and luminosity, so the period is not an arbitrary property. It is a direct readout of how much light the star is producing. Find a Cepheid in another galaxy, time it for a few weeks, and you have a standard candle. Every distance beyond the reach of parallax, including the last 3 entries on this list, sits on a ladder whose first rung is a relation found by a woman reading photographic plates for 30 cents an hour. The modern distance is 2.537 million light-years, established now by several independent methods that agree with each other, including Cepheids, the brightness of the brightest red giants, and eclipsing binary stars measured directly inside Andromeda itself. The galaxy holds roughly 1 trillion stars, which is more than the Milky Way, spread across a disk about 220,000 light-years wide. It is also coming toward us, and this is where the honest version differs from the popular one. Andromeda's motion along our line of sight is well measured. It is approaching at about 110 kilometers per second. What is not well measured is its sideways motion, and that is what determines whether the two galaxies strike each other centrally or sail past at a distance. Measuring the sideways drift of an object 2.5 million light-years away requires detecting an angular shift of a few tens of microarcseconds, which is at the edge of what any instrument can do. Hubble Space Telescope measurements published in 2012 favored a direct merger in about 4 billion years, and that became the standard story. Work published in 2025, using improved data and properly accounting for the gravitational pull of the Large Magellanic Cloud, found the outcome much closer to a coin flip, with a merger inside the next 10 billion years at roughly even odds. The honest answer today is that we do not know, and the number has moved more than once. What is certain is what happens to the stars when it does occur, and we established that 2 entries ago. Nothing hits anything. 2 galaxies containing 1.5 trillion stars between them will pass through one another and rearrange each other completely without a single stellar collision. There are details in Andromeda worth carrying. It has at least 14 satellite galaxies of its own, 2 of which, M32 and M110, are bright enough to see in a modest telescope. Its core contains a double nucleus, resolved by Hubble the telescope rather than Hubble the man in 1993, which turned out to be a lopsided disk of stars orbiting a black hole of roughly 100 million solar masses. Its disk is warped, and the arrangement of its globular clusters suggests it went through a major merger of its own around 2 billion years ago. There is a third large member of the local group, and it is worth mentioning because it extends the naked eye claim slightly further. The Triangulum galaxy, catalogued as M33, sits at about 2.7 million light-years. Under genuinely exceptional conditions, from a very dark site, with fully dark-adapted eyes and knowledge of exactly where to look, some observers can detect it. It is right at the boundary of what the human eye can do, and reports of successful sightings have been argued over for a century. It is also worth being clear about what the eye is actually receiving from Andromeda. The photons entering a person's retina from that galaxy left 1 trillion different stars, spread across 200,000 light-years, at a range of dates spanning tens of thousands of years, and traveled independently for 2.5 million years before arriving within a fraction of a second of each other at the same square centimeter of tissue. The smudge is not an image of a galaxy. It is an average of one, assembled by the geometry of a very long journey. But the most useful fact about Andromeda is the plainest one, and it is worth ending on. It is the farthest thing a person can look at directly, on any clear dark night, with no equipment of any kind. And it is the second nearest large galaxy in a universe that contains something on the order of 2 trillion of them. Everything past this point is either bound to us or leaving us. And the space in between is emptier than anything that has ever been built. Number 5. The emptiest place that exists. The local group spans about 10 million light-years and contains somewhere between 50 and 80 known galaxies. 2 of them account for almost all the mass, the Milky Way and Andromeda. The Triangulum galaxy is a distant third. Everything else is a dwarf, and most of the dwarfs orbit one of the 2 large members. 24 new ones have been identified since around 2015, and several of them are so faint that they contain fewer stars than a single globular cluster. This is the last structure on the list that is permanently bound to us. The distinction matters more than it sounds. The local group's own gravity is strong enough to overcome the expansion of space within it. Everything inside stays inside. Everything outside is receding and will keep receding faster. In roughly 100 billion years, the merged remnant of the local group will be, for anyone inside it, the entire visible universe. That is not a speculative model. It follows directly from the expansion rate we have measured and the mass we have weighed. Between the galaxies is the emptiest environment that exists anywhere. The intergalactic medium in the outer regions of the local group holds on the order of 1 atom per cubic meter. 1. A single hydrogen nucleus and its electron in a volume roughly the size of a domestic washing machine with nothing else in it. It is worth putting that number beside a laboratory one, because the comparison is the whole point of this entry. The best ultra-high vacuum that human engineering can produce reaches pressures around 10 to the minus 12 pascals. At room temperature, that still leaves roughly 240 million molecules in every cubic meter. 240 million in the emptiest chamber ever built, after every pump and trap and bakeout has been applied. The gap between our best vacuum and ordinary intergalactic space is a factor of about 100 million. Everything humanity has ever done to remove matter from a container falls short by 8 orders of magnitude of a randomly chosen cubic meter between galaxies. And that cubic meter is not special. It is the ordinary condition of the majority of the universe by volume. The consequences of that emptiness are physical rather than poetic, and the most important of them is the reason this entire subject exists. A photon crossing intergalactic space typically encounters nothing at all. Not less scattering. Nothing. Across millions of light-years, it passes no atoms close enough to interact with, is absorbed by nothing, is deflected by nothing, and arrives carrying essentially the same information it departed with. Its wavelength has been stretched by expansion, which is a known and correctable effect, but the pattern encoded in it is intact. This is why astronomy works. Imagine intergalactic space filled to the density of the interstellar medium inside a galaxy, which is itself an extraordinary vacuum by any earthly standard. At that density, light crossing millions of light-years would be scattered and absorbed until nothing coherent survived. The universe beyond a few million light-years would be a uniform fog. Andromeda would be a blur. Everything on the last 4 entries of this list would be permanently unknowable, and no amount of instrument building would fix it. We can see 13 billion years into the past, because the space in between contains almost nothing to get in the way. The emptiness is not an obstacle to observation. It is the medium that makes observation possible. There is one qualification worth making, because the transparency is not perfect at every wavelength. Neutral hydrogen absorbs light very strongly at one particular ultraviolet wavelength, and there is enough neutral hydrogen scattered through intergalactic space in thin clouds that the spectrum of any very distant bright object arrives cut through with hundreds of narrow absorption lines. Each line marks a separate cloud the light passed through, and because each cloud sits at a different distance, each line has been stretched by a different amount. Astronomers call the result the Lyman Alpha Forest. It is a complete record of everything the light passed through on its way here, arranged in order of distance, written into a single spectrum. What began as an obstacle turned into one of the most detailed maps of the intervening universe available. The local group's internal arrangement has one further oddity. It has no clear center. Most large structures in the universe have a dominant body with everything else in orbit around it. The local group has two comparable galaxies, so its center of mass sits in open space between them, somewhat closer to Andromeda because Andromeda is heavier. Neither galaxy is the anchor. Both are orbiting a point that contains nothing. The vacuum is not literally empty, though, and the accounting turned out to be harder than expected. Cosmology predicts a certain quantity of ordinary matter, the kind made of protons and neutrons, and that prediction is well constrained by the composition of the early universe and by the pattern in the cosmic microwave background. When astronomers added up all the ordinary matter they could actually find in stars, gas and dust, they came up short. Somewhere between a third and a half of it could not be located. This was not the dark matter problem, which is separate and larger. This was ordinary matter, known to exist, that nobody could point at. The answer is a component called the warm-hot intergalactic medium. It is gas at temperatures between about 100,000 and 10 million degrees, strung along the filaments of the cosmic web, so hot that it is almost completely ionized, and so thin that it emits virtually nothing. It is essentially invisible by design. Detecting it required indirect methods, watching for the shadows it casts in the spectra of very distant bright objects behind it, and looking for the faint imprint it leaves on the cosmic microwave background passing through it. Results accumulating from around 2017 and 2018 have largely closed the gap, though the census is not finished. There is one more property of this environment, and it is thermal. The cosmic microwave background fills all of space, and it gives every point in the universe a floor temperature of 2.725 Kelvin. That is not the temperature of a place. It is the temperature of everywhere. Any object sitting in intergalactic space with no internal heat source will radiate away its warmth until it reaches that value, and then it will stop, because it is receiving as much energy from the background as it is losing. The universe has a temperature, and everywhere you go, that temperature is a little under 3 degrees above absolute zero. There is exactly one known natural exception, and it is instructive. The Boomerang Nebula sits at about 1 Kelvin, colder than the background it is embedded in. It manages this by expanding extremely rapidly, and expanding gas cools, in the same way the air escaping a pressurized canister comes out cold. It is a refrigerator running on its own outflow, and it is the only known place in the universe colder than the universe. It cannot last. Once the expansion slows, it will warm back up to the floor like everything else. The local group's own position in all this is not restful either. It is falling toward the Virgo cluster at roughly 300 kilometers per second, and it will never arrive because the expansion between here and there is winning. There is also a large empty region immediately adjacent to us, called the local void, which is pushing our galaxy away at something like 250 kilometers per second. It exerts no force at all. It simply contains less matter than average, so everything around it is pulled away from it by the denser regions on the other side. Being pushed by an absence is going to become the theme of the remaining entries. Outside the local group, everything is falling towards something we cannot see. Number 4. Virgo, Laniakea, and being carried. The Virgo cluster is about 65 million light-years away and contains somewhere between 1,300 and 2,000 galaxies. It is the nearest large cluster, and it is the gravitational anchor of our entire region. The local group is falling toward it, along with everything else within about 60 million light-years, and Virgo's mass is Y. Its most prominent member is M87, a giant elliptical galaxy at about 55 million light-years. It holds a black hole of roughly 6.5 billion solar masses, which is around 1,500 times more massive than the one at the center of our own galaxy. That black hole produced the first photograph anyone has ever taken of an event horizon, released on the 10th of April 2019. The number worth holding from that image is not the mass. It is the angular size. The ring in that picture is about 40 microarcseconds across. To put that in something a person can picture, it is the angular size of an orange sitting on the surface of the moon, viewed from a garden on Earth. That was resolved from 55 million light-years by 8 radio observatories on 4 continents, observing simultaneously and combining their data afterwards. The observations were taken in April 2017, and it took 2 years to turn them into an image. M87 has a second feature, and it is much older. A jet of plasma extends about 5,000 light-years out from the nucleus, and it was first photographed in 1918 by Heber Curtis, who described it as a curious straight ray. That is the same Curtis who 2 years later would stand up at the Great Debate and argue that the spiral nebulae were separate galaxies. He photographed a relativistic jet from a supermassive black hole 4 decades before anyone had a concept of either thing. Material in that jet appears to move at several times the speed of light. It does not. The jet is pointed almost directly at Earth, and when a source moves nearly toward an observer at close to light speed, the light it emits arrives compressed in time, making the apparent motion across the sky exceed the real motion. It is a geometric illusion with a completely understood cause, and it has been under continuous observation for over a century. There is also a counterjet, pointing in the opposite direction, and it is almost invisible for the same geometric reason. Light from a source moving rapidly away is beamed backward, away from the observer, and dimmed. The jet we can see and the jet we cannot are physically the same phenomenon, and the difference between them is entirely a matter of which way each one happens to point relative to us. The event horizon measurement settled an argument as a side effect. Before the image, 2 competing methods for weighing M87's black hole disagreed by roughly a factor of 2, one giving around 3.5 billion solar masses and the other around 6.5. The Event Horizon Telescope's result, derived from the size of the ring, landed squarely on the higher figure. A dispute that had run for years in the literature was closed by taking a photograph of the object itself. Now zoom out, and Virgo stops being a destination and becomes a component. In September 2014, a team led by Brent Tully published a redefinition of the supercluster we belong to. The novelty was in the method. Rather than drawing boundaries around where galaxies are, they drew them around where galaxies are going. They mapped the velocities of over 8,000 galaxies and subtracted the uniform expansion of the universe from each one, leaving only the residual motion caused by gravity. Then they looked for the region within which all of those residual flows converge on a common point. That region has a natural boundary, in the same way a river basin does. On one side of the ridge, water flows to one sea, and on the other side it flows to another. They named the resulting structure Laniakea, from Hawaiian words meaning immeasurable heaven. It is about 520 million light-years across. It contains roughly 100,000 large galaxies. Its mass is something like 100,000 trillion suns. And until 2014, nobody knew what shape our address had. The point everything is flowing toward already had a name. The Great Attractor was inferred in 1986 by a group of astronomers who became known as the Seven Samurai, after they found that galaxies across an enormous region of sky were all moving in a coordinated way that uniform expansion could not account for. It sits somewhere between 150 and 250 million light-years away in the direction of the constellation Norma. It also sits behind the zone of avoidance, which is the band of sky blocked by the dust and stars of our own galaxy's disk. Roughly a fifth of the extragalactic sky is simply not visible in optical light because the Milky Way is in the way. The Great Attractor was inferred from the motions of things around it years before anyone could see what was there, and it took until the mid-1990s for X-ray and infrared surveys to identify the Norma cluster sitting in the right place. Then in 2017, the other half of the picture arrived, and it is the half that changes how the whole thing feels. A team including Yehuda Hoffman, Daniel Pomered, Tully, and Hélène Courtois mapped the local velocity field in 3 dimensions and identified something on the opposite side of the sky from the Great Attractor. They called it the dipole repeller. It is a large, underdense region, and it pushes. It does not push in the sense of exerting a force, because underdensities cannot do that. It pushes in the sense that everything around it is pulled away from it by the denser material on the far side. The effect is identical to a repulsion, and it is not small. Our galaxy's motion through the universe is the sum of a pull from a dense region and a push from an empty one, and the empty one contributes roughly half. Half of the motion of the Milky Way is caused by a place where nothing is. The watershed analogy is worth taking seriously because it defines where we stop. On the far side of the boundary lies the Perseus-Pisces supercluster, and the galaxies over there are flowing away from ours toward a different attractor entirely. The line between the two is not marked by anything visible. There is no wall, no gap, no change in the density of galaxies as you cross it. It is a surface defined purely by which way things are moving, and a galaxy sitting exactly on it would be pulled equally in both directions. Adding the whole picture together gives our actual motion. The Milky Way moves at about 630 kilometers per second relative to the cosmic microwave background, which is the closest thing the universe offers to a fixed frame of reference. That single velocity is the vector sum of the pull from Virgo, the pull from the Great Attractor beyond it, and the push from the dipole repeller on the other side. We are being handled by 3 things at once, 2 of which we cannot see directly, and 1 of which is not there. There is a final property of Laniakea that undercuts the whole idea of it, and it deserves to be stated plainly. Laniakea is not gravitationally bound. Dark energy is accelerating the expansion of space, and the supercluster is being pulled apart faster than its own gravity can assemble it. The flows we mapped are real, and they are losing. It is a structure that can be defined, named, measured, and mapped, and it will never exist as a finished object. We arrived in time to draw the boundary of something that is coming apart. Much of the Great Attractor's mass, incidentally, remains poorly surveyed for the same reason it was hard to find in the first place. The zone of avoidance still hides a substantial fraction of it, and the total mass estimate, currently in the range of several tens of thousands of trillions of solar masses, carries a large uncertainty that will only shrink when infrared and radio surveys finish working through the obscured band. And at the next scale up, the galaxies stop being the structure. The emptiness does. Number 3. The voids and the cosmic web. Above a few 100 million light-years, the universe stops looking like a scattering of galaxies and starts looking like a structure with a shape. Matter is arranged in filaments, which are threads of galaxies and dark matter running for hundreds of millions of light years. Where filaments meet, clusters sit at the junctions. Between filaments there are sheets, called walls, which are flattened concentrations spread across enormous areas. And between all of it, there are voids. By volume, the voids are the universe. They occupy roughly 80% of it, and everything on this list up to now, every star, every galaxy, every cluster, is packed into the remaining 20. The Boötes void is the standard example, and it has been since it was found. In 1981, a team including Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman were conducting a redshift survey, measuring the distances to galaxies in several patches of sky. In one direction, in the constellation Boötes, they found a region roughly 330 million light-years across, about 700 million light-years away, that was almost entirely vacant. Based on the average density of the universe, a volume that size should contain around 2,000 galaxies. They found about 60. Now the fact from this entry that is worth carrying for the rest of your life. Suppose the Milky Way sat at the center of the Boötes void, instead of where it actually is. The nearest other galaxy would be more than 150 million light-years away, which would place it far beyond the reach of any 19th or early 20th century telescope. Hubble's plate in 1923 would have shown nothing. There would have been no Cepheid to find, because there would have been no galaxy close enough to resolve individual stars in. The great debate of 1920 would have been settled the other way. Shapley would have been declared correct. Astronomers in that universe would have concluded, on excellent evidence and with sound reasoning, that the Milky Way was the entire universe, and that the fuzzy patches were all local. They would have been doing everything right, and they would have had no way to find out they were wrong, probably until sometime in the 1960s, when radio astronomy and much larger instruments finally began reaching far enough. An observer's position determines what they are able to conclude. That is not a philosophical point. It is a measurable property of where you happen to sit, and it will come back before this list is finished. The voids are not accidents or gaps in our surveys. They are the direct outcome of the way the universe started. In the earliest moments, matter was distributed almost perfectly evenly, but not quite. The variations were about 1 part in 100,000, and we can still see them today as the faint temperature ripples in the cosmic microwave background. Regions that started marginally denser had marginally more gravity, so they pulled in surrounding material and became denser still. Regions that started marginally emptier lost their material to their denser neighbors and became emptier still. The process compounds. Over 13 billion years, a difference of 1 part in 100,000 became the difference between a cluster of galaxies and a void with almost nothing in it. And it is still running. Voids are expanding faster than the universe as a whole, because they contain too little matter to slow themselves down. The empty places are becoming emptier at an accelerating rate. Galaxies that live inside voids turn out differently, which as a result nobody would have predicted from first principles. With almost no neighbors, a void galaxy experiences very few mergers. It is not stripped of its gas by passing through a hot cluster medium. It has no companions to disturb its disk. The consequence is that void galaxies tend to be bluer, smaller, richer in gas, and slower in their development than galaxies of the same age in crowded regions. They are still forming stars at rates that dense region galaxies gave up on billions of years ago. Isolation is a physical variable, and it is legible in what a galaxy becomes. There is a mild tension in the other direction as well. Early simulations of void formation predicted that voids should be nearly sterile, containing almost nothing at all, because whatever started in them should long since have drained into the surrounding filaments. Surveys have found more void galaxies than that picture allows. Not many more, but consistently more, and the discrepancy has not gone away as the surveys have improved. The emptiest regions of the universe are slightly less empty than the models say they should be, which is a small problem and a real one. The web itself was predicted before it was seen, which does not happen often. Simulations in the late 1970s and through the 1980s, run on computers with less capability than a modern phone, showed matter organizing itself into filaments and sheets around expanding voids purely under the action of gravity acting on small initial fluctuations. The prediction sat there for a decade with no way to test it. Then the redshift surveys arrived, first from the Harvard-Smithsonian Center for Astrophysics and later on an enormous scale from the Sloan Digital Sky Survey, and the maps that came out looked like the simulations. That agreement is one of the strongest pieces of evidence that the broad picture of how structure formed is correct. The filaments run to sizes that put pressure on the theory. The Sloan Great Wall, identified in 2003 from the Sloan Digital Sky Survey, extends about 1.4 billion light-years. The Hercules Corona Borealis Great Wall, proposed in 2013 from a clustering of gamma-ray burst positions, has been estimated at up to 10 billion light-years, which would make it a structure spanning a substantial fraction of the entire observable universe. That last one is genuinely disputed, and the dispute is worth understanding rather than glossing over. Standard cosmology rests on an assumption called the cosmological principle, that on sufficiently large scales the universe is uniform. Every model of the universe's expansion and history depends on it. The scale at which uniformity is supposed to take hold is around 1.2 billion light-years. Structures much larger than that should not exist, because there has not been enough time since the Big Bang for gravity to organize matter over such distances. So a coherent object 10 billion light-years long is not merely large. It is a problem for the assumption that makes cosmology solvable. Whether these structures are real coherent objects or chance alignments in sparse, patchy survey data is unresolved. Gamma-ray bursts are rare, and their positions are known imperfectly, which makes clustering claims difficult to test. Two more reported structures, the Giant Arc in 2021 and the Big Ring in 2024, both traced using absorption from magnesium in distant quasar spectra, have kept the question open rather than settling it either way. Our own address includes a hole of its own, and it is closer than any of these. The local void begins essentially at the edge of the local group and covers a large fraction of one hemisphere of the sky. It contains far fewer galaxies than models comfortably predict, even accounting for the difficulty of surveying through our own galactic plane. And as mentioned, it is pushing us away at roughly 250 kilometers per second by the simple mechanism of not being there. There are others. The Eridanus supervoid, associated with a large cold spot in the cosmic microwave background, is about 1 billion light-years across, and whether the two are connected has been argued for over a decade. A claimed local underdensity called the KBC void, perhaps 2 billion light-years across, has been proposed as a partial explanation for the persistent disagreement between different measurements of the universe's expansion rate. It is contested, and in 2023, a structure called Ho'olelana was reported, a shell about 1 billion light-years across, which may be the first individually identified example of a sound wave frozen into the distribution of matter during the universe's first 400,000 years. If that identification holds, it is a fossil of a pressure wave, still visible in the arrangement of galaxies 13 billion years later. The pattern of this list has been building since the asteroid belt, and here it completes. At every scale, the emptiness turned out to be the majority, and the substance turned out to be the exception. At this scale, The emptiness is not the background against which the universe is arranged. It is the arrangement, which is exactly the problem waiting at the far end of everything we can see. Number 2. 13 billion years of light. The James Webb Space Telescope has now identified galaxies whose light has been traveling for more than 13.4 billion years. The galaxy catalogued as JADES GSZ 14-0, confirmed in 2024, sits at a redshift of 14.32, which places it about 290 million years after the Big Bang. A galaxy reported in 2025, catalogued MZ14, sits at a redshift of 14.44, pushing that to roughly 280 million years. These are the earliest structures anyone has ever seen, and the light from them left when the universe was about 2% of its present age. Now, here is where the arithmetic stops behaving the way anybody's intuition expects. The light from JADES GSZ 14-0 traveled for 13.5 billion years. It is very tempting to conclude that the galaxy is therefore 13.5 billion light-years away. It is not. It is about 33.8 billion light-years away. The reason is that while the light was in transit, space itself expanded, and the galaxy was carried along with it. The photon crossed a gap that was small when it set out, and enormous by the time it finished. The distance it actually covered and the distance to the object it came from are two different quantities, and they differ by a factor of 2.5. The numbers make it sharper. At the moment that light was emitted, the galaxy was only about 2.2 billion light-years from the position that would eventually become ours. The universe was 15 times smaller in every dimension than it is today. So the light spent 13.5 billion years crossing what began as a gap of 2.2 billion light-years, because the gap kept lengthening underneath it the entire way. The light itself carries the record of that stretching. Ultraviolet radiation from hot young stars left that galaxy, and it arrives at the telescope as infrared, its wavelength expanded by the same factor of 15 that expanded the space it crossed. This is not a Doppler shift from motion through space. It is space itself having grown while the wave was inside it, and the wave lengthening in proportion. Every wavelength arrives 15.32 times longer than it left. There is one more layer, and it is the one that breaks intuition entirely. At the moment its light departed, that galaxy was already receding from our position faster than light. This does not violate anything, because nothing is moving through space at superluminal speed. The galaxy is not traveling. The space between the two locations is expanding, and there is no limit on how fast that can happen. The consequence is that the photon, having set out toward us, initially lost ground. For a long stretch of its journey it was moving in our direction at the speed of light, and the distance between us was increasing anyway. Only later, once the expansion rate in the intervening region had dropped sufficiently, did the photon begin genuinely closing the gap. Ride that photon for a moment. It leaves as ultraviolet from a small, bright galaxy 290 million years after the beginning, in a universe that is hot, compact, and crowded with young stars burning through their fuel at a furious rate. It sets out toward a position 2.2 billion light-years away, and for the first stretch of its journey, it goes backwards, carried away faster than it can travel. Space stretches beneath it continuously. Its wavelength lengthens and lengthens again. Around it, the universe grows old and cold and sparse, galaxies assembling and merging and settling, the light of the first stars fading into the light of later ones. It passes through voids and filaments and encounters essentially nothing. 13.5 billion years after it left, it strikes a 6.5-meter mirror of gold-coated beryllium, held at 40 degrees above absolute zero, 1.5 million kilometers from a planet that did not exist when it set out, and will not last as long as it has already traveled. None of this would be observable without one specific piece of engineering. The reason the Hubble Space Telescope could not see these objects is not that it lacks resolution. It is that the light arrives as infrared, and Hubble was not built to work far into the infrared. The James Webb Space Telescope was. Its 6.5-meter mirror is coated in gold because gold reflects infrared efficiently. It operates at about 40 Kelvin, shielded from the sun by a 5-layer sun shield the size of a tennis court, because a warm telescope glows in the infrared and would drown out everything it was trying to see. It sits 1.5 million kilometers from Earth, precisely so it can stay that cold. Every one of those design choices exists to catch light that left the universe as ultraviolet and arrived as something else entirely. The galaxies themselves are small. Objects at these redshifts are typically 1,000 times less massive than the Milky Way and only a few hundred to a couple of thousand light-years across, which is a fraction of a percent of our galaxy's width. They are being detected across 33 billion light-years because they are extraordinarily luminous for their size, packed with hot young stars, burning at rates no galaxy today sustains. What those early galaxies look like is a separate problem, and an unresolved one. They are too bright and too developed for the time available. Standard models allow a few 100 million years to assemble a galaxy of the luminosity being observed, and the objects being found appear to have managed it faster. The candidate explanations include unusually efficient star formation in the early universe, an early generation of very massive stars producing far more light per unit mass, and black hole accretion contributing a larger share of the light than assumed. None is settled. A population of compact red sources found in large numbers, informally called the little red dots, remains unexplained after several years of work. Behind all of these galaxies there is a wall. Look far enough and there are no galaxies to see, because there were not yet any galaxies. At about 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, free electrons scattered light constantly, and the universe was opaque, like the interior of a fog. At that moment, the fog cleared, and the light that had been trapped was released in all directions. That release is the cosmic microwave background, and it is still arriving. It was found by accident. In 1964, Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey with a horn antenna built for satellite communications, and they had a persistent hiss they could not eliminate. It came from every direction equally, day and night, in every season. They checked the electronics. They checked the joints. They found a pair of pigeons nesting in the horn, evicted them, and cleaned out what the pigeons had left behind. The hiss remained. After roughly a year of elimination, they concluded the noise was not in the instrument at all. A team at Princeton, a few kilometers away, was at that moment building an instrument specifically to look for the radiation left over from a hot early universe. They had worked out that it should exist and what temperature it should have. They were beaten to it by two engineers who were trying to get rid of it. Penzias and Wilson shared the 1978 Nobel Prize in Physics. The background sits today at 2.725 Kelvin, and the surface it comes from is about 45.6 billion light-years away in present-day terms. It is uniform to about 1 part in 100,000, and those tiny variations are the seeds from which every structure on this entire list grew. There is one thing further back than the microwave background, and we will almost certainly never see it. About 1 second after the Big Bang, long before the universe became transparent to light, it became transparent to neutrinos. Those neutrinos are still here, filling space at a density of something like 336 per cubic centimeter, cooled now to under 2 Kelvin. They constitute a second background, older than the light one by 380,000 years, and they pass through everything without interacting, Detecting them would mean seeing the universe at 1 second old. Several proposals exist. None is close to working. The period between the microwave background and the first galaxies has a name, and Just is currently inside it. For a long stretch after the fog cleared, the universe was filled with neutral hydrogen, and there were no stars, and it is called the Dark Ages for exactly that reason. Then the first stars formed, and their ultraviolet light began ionizing the hydrogen around them, clearing bubbles that grew and merged until the whole universe was transparent again. That process, called reionization, ran from roughly 200 million to 1 billion years after the beginning. The galaxies at redshift 14 are inside it, and they are the sources doing the clearing. Which brings us to the number that sounds like a contradiction and is not. The observable universe is 93 billion light-years across, and the universe is 13.8 billion years old. Those two figures are both correct. The universe is not larger than light could have crossed. The container grew while the message was inside it, and the message arrived from a place that had been carried much farther away in the meantime. And every number on this list so far describes only the part of the universe that light has had time to reach. Number 1. Everything beyond the observable. The observable universe is 93 billion light-years across. That figure is not the size of the universe. It is the size of the region from which light has had time to reach us during the 13.8 billion years the universe has existed, corrected for the expansion that occurred while the light was traveling. It is a statement about our position and our age. It says nothing whatsoever about how big the thing itself is. It is also centered on the observer, which means every point in the universe has its own observable region, and they mostly do not overlap. A galaxy at the edge of ours has an observable region of the same size centered on itself, extending 46 billion light-years past our boundary in the opposite direction. That region contains material we will never see, from a place that is itself at the limit of what we can see. So the first question is how much more there is. And there is a way to get at it that does not require going there. If the universe is curved, that curvature would leave a signature. A triangle drawn across the sky on a curved surface has angles that sum to more or less than 180 degrees, and the pattern of hot and cold spots in the cosmic microwave background provides a triangle of known physical size at a known distance. Measure how large those spots appear, compare with how large they should be, and the difference gives the curvature. The Planck spacecraft's measurements, released through 2018, found the universe flat to within about 0.25%. No detectable curvature at all. Now, a sphere looks flat when you examine a small enough piece of it. Stand in a field and the Earth appears flat, because the field is small compared with the planet. The flatter the piece looks, the larger the sphere has to be. So a measurement of flatness to 0.25%, taken across a region 93 billion light-years wide, translates directly into a lower bound on the size of the whole. The bound is roughly 250 times the diameter of the observable region. That is a flaw, not a measurement. It means at minimum something like 15 million times the volume of everything we can see, and the actual answer could be anything above it. Inflation pushes the number much higher. If the very early universe underwent the brief episode of exponential expansion the theory requires, then the region we can observe is a small patch of something enormously larger, and the standard estimate puts the ratio at something on the order of 10 to the 23rd in radius. Written out, that is 100,000 billion times larger than everything we can see. And in the simplest inflationary models, the answer is not a large number at all. It is that the universe is infinite, and the observable region is not a small fraction of it. It is a fraction of 0. That is the first problem. The second one is worse, because it does not concern the parts we cannot see. It concerns the parts we can. The expansion of the universe is accelerating, driven by whatever dark energy turns out to be, and acceleration creates a boundary. There is a distance, called the cosmic event horizon, at roughly 16 billion light-years in present-day terms, beyond which light emitted today will never arrive here. Not slowly, not eventually. Never, no matter how much time passes, because the space in between grows faster than the light can cross it. Of the roughly 2 trillion galaxies estimated to lie within the observable universe, something like 94% are already past that line. Their light from the past is still arriving. We can photograph them, measure them, catalogue them, and study them in detail. Nothing they emit from this moment onward will ever reach us. They are visible and permanently gone at the same time, and those two facts are not in conflict, because what we are seeing is a record rather than a place. The line for reaching them is at about redshift 1.7. Everything beyond that is out of contact, permanently. A message sent from here today, at light speed, in any direction, could never arrive at 94% of the galaxies we can currently see. And the horizon is closing. As the expansion accelerates, galaxies cross out of reach steadily, at a rate on the order of 1 per second. The local group stays because it is gravitationally bound and expansion does not operate inside bound systems. Everything else goes. It is worth separating two horizons that get confused because they are different distances doing different jobs. The particle horizon, at about 46.5 billion light-years, defines what we can see. Everything inside it has had time to send light that has arrived. The event horizon, at about 16 billion, defines what we can ever affect or be affected by from this moment forward. The gap between those two numbers is the entire population of galaxies that we can observe and can never touch, and it is most of them. The acceleration that produces this was not predicted and was not wanted. In 1998, two competing teams measuring distant supernovae to determine how quickly the expansion was slowing down both found that it was not slowing down at all. It was speeding up. Neither team believed its own result at first, and each checked partly in the hope of finding the other's error. They found the same thing. The discovery earned the 2011 Nobel Prize in Physics, and it converted the fate of the universe from an open question into a closing door. There is one live uncertainty in this picture that is worth flagging honestly. All of these projections assume dark energy has a constant strength. Some recent large survey results have hinted that it might change over time. If it does, the horizon's future behavior changes with it, and the timeline for everything described below would shift. The hint is not confirmed, and the significance is not yet decisive. The direction of the conclusion, though, is not in serious doubt. The end state follows directly from measurements already made, and it is worth stating plainly. In roughly 150 billion years, the galaxies outside the local group will have redshifted so far that no instrument could detect them. In a few 100 billion years, the merged remnant of the Milky Way and Andromeda will sit alone, with an apparently empty sky beyond its own stars. Stand there for a moment. It is a world orbiting a long-lived red dwarf in a large elliptical galaxy that formed from a merger nobody remembers. The night sky holds the stars of that one galaxy and nothing else. Their telescopes are excellent. Their physics is correct, and it is the same physics we have. They observe carefully, and they find one galaxy. They look for a microwave background and find nothing, because it has been stretched to wavelengths so long that no detector of any conceivable design could register them. They measure the motions of their stars and find a stable, bound, unchanging system. They look for evidence that space has ever expanded and find none, because every piece of that evidence has been carried past the horizon. They conclude that they live in a single static island in an eternal void. It is the only conclusion their observations support. They are doing everything right, and there is no measurement available to them anywhere, ever, that could show them otherwise. We have met that observer before on this list. 2 entries ago, standing at the center of the Boötes void, doing careful science and concluding that their galaxy was the whole universe. That was not a curiosity. It was a preview. So this is the last distance on the list, and it is the only one that cannot be given a number. Not because it is too large to write down. Numbers that large are easy to write. It is because the information required to write it sits on the wrong side of a horizon, and no instrument built at any point in the future will change that. Every other entry on this list is knowable for one reason. The Moon at 384,000 kilometers, the Sun at 8 light minutes, Proxima at 4.2 light years, Andromeda at 2.5 million, the first galaxies at 33 billion. Every one of them is a number we possess because light made the trip. That was the method from the very first entry. This one is defined precisely by light not making the trip. It is the same method, inverted, and the inversion is permanent. 19 entries of this list added up to the observable universe. The 20th is the recognition that the observable universe is, as far as anyone can tell, the small part. There is a version of this that sounds bleak, and I do not think it is the right reading. The arrangement is temporary in one direction only. We happen to be alive at a moment when the evidence is still arriving, when the background radiation is still detectable, when 2 trillion galaxies are still in the sky, when the expansion is still measurable from the inside. That window is not permanent, and it did not have to include us. A civilization 100 billion years from now gets none of it. A civilization inside a void gets very little of it. We got the whole thing at the one point in the history of the universe when it was still legible. And here is the last thing worth saying, at the end of 3 hours of distances that do not fit in a human mind. Not one of them requires anything of you. The nearest star will still be 4 light years away in the morning. 94% of the galaxies will still be out of reach, exactly as they have been for your entire life, and exactly as they were for everyone who came before you and never knew it. Nothing on this list is a problem to be solved tonight, or a distance you have to close. The only one that ever mattered on any given evening is the very first one on the list. 384,000 kilometers to the Moon, 1.25 seconds of light, close enough to see from a window. Let the rest of it stay where it is. It has been managing without us for 13 billion years, and it will manage for a while longer. Sleep well, and good night.